In the 1st century of the Common Era, in the city of Alexandria, Egypt, a Greek engineer named Heron built a device that changed the world. Or rather, it should have changed the world. It did not. The device was a hollow metal sphere, mounted on a pair of pivots above a sealed cauldron of boiling water. Steam from the cauldron rose through the pivots into the sphere, and then escaped through 2 small, bent nozzles on opposite sides of the sphere. As the steam escaped, the reaction force of the jet caused the sphere to spin on its axis, rotating with increasing speed as the steam pressure built. Heron had built a steam engine. He had built a device that converted heat energy into rotational motion, the fundamental principle that would eventually power the Industrial Revolution, drive the locomotives that connected continents, propel the ships that crossed oceans, and generate the electricity that illuminated the modern world. He had built this device approximately 1700 years before James Watt patented his improved steam engine in 1769. He had demonstrated the principle that would transform human civilization from an agricultural society into an industrial one. And then, as far as the historical record is concerned, nothing happened. The Aeolipile, as Heron's device is known, was described in his treatise Pneumatica, a comprehensive catalogue of mechanical devices that use steam, water, and air pressure to produce various effects. The Aeolipile was one of approximately 80 devices described in the treatise, and Heron appears to have regarded it as a curiosity, a demonstration of the motive power of steam, rather than as a practical machine. The device was not developed into a power source. It was not connected to any useful work. It was not used to pump water, to grind grain, to drive machinery, or to perform any of the countless tasks that steam engines would eventually perform in the modern world. The spinning sphere sat on its cauldron, hissing and rotating, demonstrating a principle of enormous potential significance, and then it was set aside, and the potential was left unrealized for 17 centuries. The question of why the ancient world did not develop the steam engine is one of the most provocative and most debated questions in the history of technology. The Aeolipile demonstrates that the basic principle of steam power was known in the ancient world. The engineering tradition of Alexandria, which was the most sophisticated in the ancient world, was capable of building complex mechanical devices that exploited the properties of steam, water, and air pressure. The demand for mechanical power, which was supplied in the ancient world by human labour, by animal labour, and by the limited power of water wheels and windmills, was enormous. And yet the steam engine was not developed. The spinning sphere remained a curiosity, and the Industrial Revolution was delayed by 17 centuries. By the end of tonight, you are going to understand what the Aeolipile was, how it worked, who Heron was, and what he achieved, and why the ancient world failed to develop the steam engine, despite having the basic principle in hand. You are going to learn about the specific technological, economic, social, and intellectual conditions that prevented the ancient world from exploiting the potential of steam power, and you are going to see how the failure to develop the steam engine is connected to the broader story of lost and unrealized technology that has been a recurring theme in the history of human civilization. And you are going to confront a question that is as relevant to the modern world as it is to the ancient one. What determines whether a technological discovery is developed into a transformative technology, or whether it is set aside and forgotten? Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. The Aeolipile spun. The steam hissed. The sphere rotated on its axis in a workshop in Alexandria 2,000 years ago, and the world waited 17 centuries for someone to take the next step, to connect the spinning sphere to a pump or a wheel or a loom, to harness the power of steam for practical work. The wait was not necessary. The knowledge was there. The principle was demonstrated. The engineering was possible, and yet the step was not taken. The story of why it was not taken is one of the most important and most humbling stories in the history of human technology. Now, let us begin. The gap between the ancient demonstration and the modern application is one of the most striking anomalies in the history of technology. We are not talking about a principle that was hidden or obscure, locked away in an encrypted text or in a private notebook. The Aeolipile was described in a published treatise that was copied, studied, and circulated throughout the ancient and the medieval worlds. The principle was available to any engineer who could read Greek or Arabic. The demonstration could be replicated by any craftsman who could build a metal sphere and a cauldron, and yet for 17 centuries no one took the next step. No one connected the spinning sphere to a mill or a pump or a loom. No one asked the question that seems, from the modern perspective, so blindingly obvious. If steam can spin a sphere, what else can it do? The failure to ask that question, or rather, the failure to answer it in a way that led to practical development, is one of the deepest puzzles in the history of human civilization. It is a puzzle that touches on the most fundamental questions about the nature of progress, about the relationship between knowledge and action, and about the conditions that determine whether a civilization advances or stagnates. The Aeolipile is a small device, easily held in two hands, but the questions it raises are enormous, and the answers to those questions illuminate not just the history of steam power, but the history of human technology as a whole. To understand the Aeolipile and the world that produced it, we must first understand Alexandria, the city where Heron lived and worked, and the extraordinary intellectual tradition that made Alexandria the most important centre of scientific and technological innovation in the ancient world. Alexandria was not merely a city. It was an institution, a monument to the idea that the systematic pursuit of knowledge was among the highest purposes of human civilization, and the resources that were devoted to this pursuit in Alexandria were, by the standards of the ancient world, staggering. Alexandria was founded by Alexander the Great in 331 before the Common Era, on a strip of land between the Mediterranean Sea and Lake Mareotis in the Nile Delta of Egypt. The city was designed from its inception as a centre of commerce, of culture, and of learning, and the Ptolemaic dynasty that ruled Egypt after Alexander's death invested enormous resources in making the city the intellectual capital of the Hellenistic world. The Library of Alexandria, which was the most famous institution in the ancient world, was established by the early Ptolemaic kings as a comprehensive collection of the written knowledge of all civilizations, and it attracted scholars from across the Mediterranean and beyond who came to study, to teach, and to conduct research in every field of intellectual inquiry. The Mausian, the research institution that was associated with the library, was the closest equivalent in the ancient world to a modern university or a modern research laboratory. The Mausian provided scholars with salaries, with housing, with meals, and with access to the library's unparalleled collection of books and manuscripts, freeing them from the economic pressures that would otherwise have limited their ability to devote themselves to study and to research. The scholars of the Mausian conducted research in mathematics, in astronomy, in physics, in medicine, in geography, in philology, and in a wide range of other fields, and they produced some of the most important intellectual achievements in the history of human civilization. The tradition of mechanical engineering and pneumatics in which Heron worked was one of the most distinctive and most productive intellectual traditions of the Alexandrian school. The Alexandrian engineers, who combined the theoretical knowledge of Greek mathematics and physics with the practical skills of Egyptian and Near Eastern craftsmanship, developed a remarkable range of mechanical devices that exploited the properties of steam, water, air pressure, and mechanical linkages to produce effects that astonished their contemporaries and that continue to fascinate modern engineers. The first major figure in the Alexandrian mechanical tradition was Ctesibius, who lived and worked in Alexandria in the 3rd century before the Common Era, approximately 2 centuries before Heron. Ctesibius is credited with the invention of the force pump, the water clock, the hydraulic organ, and a variety of other pneumatic and hydraulic devices that demonstrated a sophisticated understanding of the properties of fluids and gases. Ctesibius's inventions were both practical and theoretical, addressing real-world problems such as the measurement of time and the supply of water, while also demonstrating the physical principles that governed the behavior of fluids under pressure. Ctesibius's work established the intellectual framework and the practical tradition within which Heron would later work, and his inventions were the foundation on which Heron built his own, more elaborate contributions. The second major figure was Philo of Byzantium, who lived in the 2nd century before the Common Era, and who wrote a comprehensive treatise on mechanical devices that included descriptions of automata, of pneumatic devices, and of military machines. Philo's treatise, parts of which survive in Arabic translation, provides detailed descriptions of devices that use air pressure, water pressure, and mechanical linkages to produce a variety of effects, including self-filling cups, automatic wine dispensers, and mechanical birds that sing and drink water. Philo's work, which was more practically oriented than Ctesibius's, provided Heron with a catalogue of devices and techniques that he could study, improve upon, and extend. Heron himself is one of the most enigmatic figures in the history of ancient science and technology. His dates are uncertain, with scholars placing his active period in the 1st century of the Common Era based on an astronomical observation that he recorded, and that has been dated to 62 of the Common Era. His biography is essentially unknown, beyond the fact that he lived and worked in Alexandria and that he was associated with the Mautian or with a similar institution. But his writings, which survive in multiple manuscripts, in Greek and in Arabic translation, provide a comprehensive picture of his intellectual interests and his technical capabilities. Heron's surviving works include treatises on pneumatics, on mechanics, on automata, on the measurement of geometric figures, on the construction of siege engines, and on the design and the calibration of a variety of instruments for surveying, for measuring, and for observing. The range of Heron's interests is extraordinary, encompassing both the theoretical and the practical, the mathematical and the mechanical, the recreational and the utilitarian. Heron was not merely an engineer or merely a mathematician. He was a polymath, a scholar who worked at the intersection of theory and practice, and who saw no contradiction between the pursuit of abstract knowledge and the construction of practical devices. The Pneumatica, which is the work that contains the description of the Aeolipile, is a catalogue of approximately 80 devices that use steam, water, air pressure, and the properties of the vacuum to produce various effects. The devices described in the Pneumatica range from the simple to the complex, from a vessel that pours water when its handle is lifted to an elaborate automatic theatre that performs a miniature dramatic scene using a system of ropes, pulleys, and counterweights driven by a descending weight. The Pneumatica is not a theoretical treatise. It is a practical manual, a collection of designs that are described in sufficient detail that they could be built by a competent craftsman, and many of the devices described in the Pneumatica have been successfully reconstructed by modern engineers. The specific description of the Aeolipile in the Pneumatica is relatively brief, occupying only a few paragraphs in the treatise. Heron describes a hollow sphere that is mounted on 2 pivots above a cauldron of boiling water. The pivots are hollow, allowing the steam from the cauldron to enter the sphere. 2 bent nozzles on opposite sides of the sphere allow the steam to escape, and the reaction force of the escaping steam causes the sphere to rotate. The description is accompanied by a diagram that shows the arrangement of the components, and that has been used by modern engineers as the basis for their reconstructions of the device. The physics of the Aeolipile is the physics of the reaction engine, the same principle that powers modern jet engines and rocket motors. When steam escapes through the bent nozzles, it carries momentum in the direction of the jet. By Newton's third law of motion, for every action there is an equal and opposite reaction, and the escape of the steam in one direction produces a force on the sphere in the opposite direction. The 2 nozzles, which are positioned on opposite sides of the sphere and which are bent in opposite directions, produce forces that combine to create a torque that rotates the sphere on its axis. The faster the steam escapes, the greater the torque, and the faster the sphere rotates. The power output of the Aeolipile, which has been estimated by modern engineers based on reconstructions of the device, is small, probably in the range of 1 to 2 watts, which is roughly equivalent to the power output of a human being pedaling a bicycle very slowly. The low power output is a consequence of the inefficiency of the device, which converts only a tiny fraction of the heat energy of the steam into rotational energy, with the rest being lost to friction, to the cooling of the steam, and to the inefficiency of the reaction nozzles. The efficiency of the Aeolipile has been estimated at less than 1%, which is far lower than the efficiency of modern steam engines, which can achieve efficiencies of 20 to 40%. The low power output and the low efficiency of the Aeolipile are among the factors that are cited by historians and engineers as explanations for why the device was not developed into a practical power source. A device that produces 1 to 2 watts of power is not useful for any practical purpose because the power output is too small to drive any meaningful mechanical load. The development of the Aeolipile into a practical steam engine would have required fundamental improvements in the design, including the replacement of the reaction nozzles with a piston and cylinder mechanism, the development of a condenser to recover the waste heat, the improvement of the seal between the moving and the stationary parts, and the use of higher steam pressures to increase the power output. These improvements, while they were within the theoretical capabilities of Alexandrian engineering, were not made, and the reasons why they were not made are the central question of the Aeolipile story. The broader context of power technology in the ancient world provides essential background for understanding the significance of the Aeolipile and the failure to develop it. The ancient world relied on 3 primary sources of mechanical power: human muscle, animal muscle, and the energy of flowing water. Human and animal labor powered the agriculture, the manufacturing, the construction, and the transportation of the ancient world, and the availability of labor was the primary constraint on the scale of economic activity. The watermill, which was invented in the Hellenistic period, and which used the energy of flowing water to drive a millstone for grinding grain, was the most important mechanical power source of the ancient world. But its use was limited to locations where a suitable water flow was available, and its power output was limited by the volume and the velocity of the water. The demand for mechanical power in the ancient world was enormous, and the failure to develop a new power source, such as the steam engine, that could supplement or replace human and animal labor, had profound consequences for the development of ancient civilization. The reliance on human labor, which included the widespread use of slave labor in the Greek and Roman worlds, shaped the social structure, the economic organization, and the technological priorities of the ancient world in ways that influenced every aspect of life. The question of whether the availability of slave labor reduced the incentive to develop labor-saving technology, and whether this reduced incentive was a factor in the failure to develop the steam engine, is one of the most debated questions in the economic history of the ancient world. The intellectual environment of Hellenistic Alexandria was shaped by the specific circumstances of the city's founding and by the cultural policies of its Ptolemaic rulers. Alexander the Great, who founded the city in 331 before the Common Era, envisioned it as a center where Greek culture would be transplanted to the ancient land of Egypt, creating a fusion of Greek intellectual traditions with Egyptian practical knowledge that would produce a new and more powerful form of civilization. The Ptolemaic dynasty, which ruled Egypt from the death of Alexander until the Roman conquest in 30 before the Common Era, pursued this vision with extraordinary dedication, investing massive resources in the construction of the library, the Moutian, and the other institutions that made Alexandria the intellectual capital of the ancient world. The scholars who worked at the Moutian represented the full range of Greek intellectual life, from the most abstract mathematicians to the most practical engineers. Euclid, who wrote the Elements, the foundational text of geometry that remained the standard mathematical textbook for over 2,000 years, worked at the Moutian in the early 3rd century before the Common Era. Archimedes, the greatest mathematician and engineer of the ancient world, studied at the Moutian before returning to his native Syracuse. Eratosthenes, who calculated the circumference of the Earth with extraordinary accuracy, served as the head librarian of the library, and the engineering tradition that produced the Aeolipile the tradition of Ctesibius, Philo, and Heron, was a central part of the intellectual life of the Maurtian, contributing to the institution's reputation as the most comprehensive centre of learning in the ancient world. The specific resources that were available to the engineers of the Alexandrian school included not only the intellectual resources of the library and the Maurtian, but also the material resources of the city's workshops and the human resources of the city's skilled craftsmen. Alexandria was one of the largest and most prosperous cities in the ancient world, with a population that has been estimated at between 300,000 and 1 million, and its workshops produced a wide range of manufactured goods, including textiles, papyrus, glass, metals, and the precision instruments that were needed for the Maurtians' research programs. The availability of skilled craftsmen who could build the devices that the engineers designed was an important factor in the productivity of the Alexandrian engineering tradition, because it allowed the engineers to concentrate on the design and the theory of their devices, while delegating the construction to specialists. The specific engineering capabilities that the Alexandrian tradition possessed are demonstrated by the devices that survive in the descriptions of Ctesibius, Philo, and Heron. The force pump of Ctesibius, which used a pair of reciprocating pistons to draw water through a valve and to discharge it under pressure, demonstrated the principles of piston-cylinder mechanics, valve control, and pressurized fluid delivery that would eventually be essential for the steam engine. The water clock of Ctesibius, which used a regulated flow of water to drive a system of gears and indicators that displayed the time, demonstrated the principles of regulated power delivery and of the conversion of linear motion into rotary motion. The automata of Philo and Heron, which used systems of pulleys, cams, levers, and counterweights to produce complex sequences of mechanical actions, demonstrated the principles of mechanical programming and of the conversion of stored energy into useful work. The fact that each of these individual principles, piston-cylinder mechanics, valve control, the conversion of linear motion into rotary motion, and the use of steam as a motive force, was known to the Alexandrian engineers, but that these principles were never combined into a single device that would constitute a steam engine is one of the most puzzling and most instructive aspects of the Aeolipile story. The individual components of the steam engine existed in the Alexandrian tradition. What did not exist was the concept of combining them into a system that would use steam pressure to drive a piston that would convert the linear motion of the piston into the rotary motion of a wheel, a concept that seems obvious in retrospect, but that evidently was not obvious to the Alexandrian engineers. The broader context of power technology in the Greco-Roman world deserves more detailed examination, because the specific power technologies that were available in the ancient world both shaped and limited the technological possibilities of the period. The human-powered devices of the ancient world included the treadmill, the capstan, the crane, and a variety of other machines that converted the muscular effort of human workers into mechanical work. The animal-powered devices included the horse-drawn chariot, the ox-drawn plough, the donkey-driven mill, and the various rotary devices that used animal power to grind grain, to press olives, and to perform other agricultural tasks. The water mill, which was the most important non-muscular power source in the ancient world, was invented in the Hellenistic period, possibly as early as the 3rd century before the Common Era, and it was gradually adopted across the Roman Empire over the following centuries. The watermill used the energy of a flowing stream to turn a wheel, which was connected through a system of gears to a millstone that ground grain into flour. The power output of a typical ancient watermill was approximately 1/2 to 3 horsepower, a modest but useful amount that was sufficient for the grinding of grain, and freed the human and animal labour that had previously been devoted to this task. The Barbegal mill complex, which was located near Arles in southern France, and which dates to the 2nd century of the Common Era, provides evidence of the scale to which water-powered milling could be developed in the Roman world. The complex consisted of 16 water wheels arranged in 2 parallel rows on a hillside, each driving a pair of millstones and it has been estimated that the complex could produce enough flour to feed a population of approximately 12,000 people. The Barbagol complex demonstrates that the Romans were capable of developing water power to a significant scale when the economic demand justified the investment, and it provides a baseline for evaluating the potential demand for an alternative power source such as the steam engine. The question of whether the ancient world needed a new power source and whether the steam engine would have been economically competitive with the existing power sources if it had been developed is one that has been addressed by economic historians. The answer depends on the specific application and the specific location. In locations where a suitable water flow was available, the watermill was an effective and economical power source that would have been difficult to displace with a steam engine, particularly given the low efficiency and the high fuel consumption of early steam engines. In locations where water power was not available, however, the only alternatives were human and animal labor, and the development of a steam engine that could provide continuous mechanical power in any location would have been an enormous economic advantage. The Roman mining industry, which operated extensive mines across the empire for the extraction of gold, silver, copper, iron, and other metals, is one of the specific industries in which the development of a steam-powered pump might have been economically justified. The Roman mines, particularly the gold mines of Spain and Wales and the silver mines of Laurium in Greece, required the removal of large volumes of groundwater, and the pumping technology that was available to the Roman miners, including the Archimedean screw, the bucket chain, and the water wheel-driven pump, was labor-intensive and limited in capacity. The development of a steam-powered pump that could remove water from the deepest levels of the mines would have been an enormous benefit to the mining industry, and the economic return from the increased production of precious metals might have justified the investment in the development of the technology. The failure to develop a steam-powered pump for the mining industry, despite the clear economic demand, is one of the most telling pieces of evidence against the hypothesis that the ancient world was entirely lacking in economic incentive for the development of steam power. The demand existed, the economic return would have been substantial, and yet the development was not undertaken, suggesting that the barriers to the development of the steam engine were more fundamental than the simple absence of economic demand. The specific technical details of the devices that Ctesibius invented deserve careful examination because they demonstrate the level of engineering sophistication that the Alexandrian tradition had achieved centuries before Heron, and because they identify the specific engineering principles that were available to the Alexandrian engineers, but that were never combined into a steam engine. The force pump of Ctesibius, which consisted of 2 cylinders with reciprocating pistons connected to a rocking beam, was a sophisticated hydraulic device that demonstrated the principle of converting rotary or reciprocating mechanical motion into the pressurized flow of a fluid. The pump used check valves to control the direction of the water flow, admitting water into the cylinder on the suction stroke and discharging it under pressure on the compression stroke. The design of the force pump is essentially the reverse of a reciprocating steam engine. The pump uses mechanical motion to pressurize a fluid, while the steam engine uses pressurized fluid to produce mechanical motion. The fact that Ctesibius could build a pump that worked in one direction, but that no one thought to build a device that worked in the other direction, is one of the most tantalizing what-ifs in the history of technology. The hydraulic organ of Ctesibius, which used a water-sealed air reservoir to maintain a constant air pressure that was delivered to a rank of organ pipes, demonstrated the principle of using fluid pressure to produce a controlled and sustained energy output. The organ used a bellows to pump air into a sealed chamber that was partially filled with water, and the weight of the water maintained a constant pressure on the air that was delivered to the pipes. The hydraulic organ was a practical device that was widely used in the Roman world for entertainment and for ceremonial purposes, and its design demonstrated a sophisticated understanding of the principles of fluid mechanics that would have been relevant to the development of a steam engine. the water clock of Ctesibius, which used a regulated flow of water to drive a system of gears and mechanical indicators, demonstrated the principle of converting the energy of a flowing fluid into the mechanical motion of a gear train. The clock used a float that rose as water accumulated in a receiving vessel, and the rise of the float was transmitted through a system of gears and pointers to a display that indicated the time. The water clock was one of the most accurate timekeeping devices in the ancient world, and its design demonstrated the principle of energy conversion that is central to the operation of a steam engine. The question of why these individual components, the piston, the valve, the pressurized fluid, and the gear train, were not combined into a steam engine, is one that has been debated by historians of technology for decades. The most commonly cited explanation is that the concept of combining these components into a system that would use steam pressure to drive a piston that would produce continuous mechanical work was a conceptual leap that the ancient engineers simply did not make, not because they were incapable of making it, but because their intellectual framework did not suggest it. The ancient engineers thought of these components as solutions to specific, individual problems, not as elements of a larger system, and the idea of combining them into a general-purpose power source was not part of their conceptual vocabulary. The specific working conditions of the Alexandrian workshops where Heron's devices were built have been inferred from the archaeological evidence of ancient workshops and from the descriptions in Heron's own texts. The workshops were equipped with furnaces for heating and melting metals, with anvils and hammers for forging, with lathes for turning cylindrical parts, and with a variety of hand tools for cutting, filing, and polishing. The metals that were available to the Alexandrian engineers included bronze, which was the primary engineering metal of the ancient world, iron, which was used for tools and for structural components, lead, which was used for seals and for fluid handling applications, and the precious metals gold and silver, which were used for decorative and for ceremonial purposes. The precision of the metalworking that the Alexandrian engineers could achieve is demonstrated by the surviving artifacts of the Hellenistic period, including the Antikythera mechanism, which we have discussed in a previous episode, and the precision instruments that were used by the astronomers and the surveyors of the period. The gear teeth of the Antikythera mechanism, which are cut with a precision that implies the use of a lathe and a dividing mechanism, demonstrate that the Hellenistic metalworkers could produce mechanical components of considerable accuracy. The precision instruments of the period, including the dioptra, the astrolabe, and the groma, demonstrate that the Hellenistic engineers could produce instruments with graduations and with moving parts that required careful alignment and precise fitting. The question of whether the metalworking precision that was available to the Alexandrian engineers was sufficient for the construction of a practical steam engine is one that has been debated by historians of technology and by mechanical engineers. The consensus is that the precision was probably sufficient for the construction of a low-pressure steam engine in which the piston cylinder fit does not need to be extremely tight because the steam pressure is low, but that it would have been insufficient for the construction of a high-pressure steam engine in which the precision of the piston cylinder fit is critical for preventing the leakage of steam. The distinction between low-pressure and high-pressure steam engines is important because the low-pressure engine, while it is less efficient and less powerful than the high-pressure engine, is also less demanding in terms of the precision and the materials that are required for its construction. The question of whether a low-pressure steam engine built with the materials and the precision available to the Alexandrian engineers could have produced useful power is one that has been addressed through theoretical analysis and through the construction of experimental prototypes. The analysis suggests that a low-pressure steam engine of modest size, operating at a pressure of approximately 2 to 3 times atmospheric pressure and driving a piston of approximately 10 centimeters in diameter, could produce a power output of approximately 1/10 to 1/4 of a horsepower, sufficient for small-scale applications such as pumping water or grinding grain. The construction of such an engine while it would have been challenging with ancient technology, was not beyond the capabilities of the Alexandrian engineers, who had demonstrated their ability to build precision mechanical devices in other contexts. The relationship between the Aeolipile and the other steam-powered devices described in Heron's Pneumatica provides important context for understanding the range of steam applications that the Alexandrian engineers had explored. The Pneumatica describes several devices in addition to the Aeolipile that use steam as a motive force, including the automatic temple doors that we have already discussed, a device that uses steam to produce the sound of a trumpet, and a device that uses steam to blow a ball into the air from a jet. These devices demonstrate that Heron was aware of the motive power of steam, and that he had explored multiple applications of this power, from the rotational motion of the Aeolipile to the linear motion of the trumpet sound and the ballistic motion of the ball. The range of applications suggests that Heron was systematically investigating the capabilities of steam as a motive force, even if he did not develop any of the applications into a practical power source. The trumpet device described in the Pneumatica is particularly interesting because it demonstrates the use of steam to produce a linear jet of significant force. The device consists of a sealed vessel of water that is heated by a fire, with the steam being directed through a tube into a trumpet that produces a loud sound. The sound is produced by the vibration of the air column in the trumpet that is driven by the pressure of the steam, and the device demonstrates that the Alexandrian engineers understood that steam could be used to produce a directed, powerful jet that could perform work on a distant object. The principle of the directed steam jet is the same principle that is used in modern steam turbines, and Heron's demonstration of this principle in the trumpet device is another example of the proximity of the Alexandrian engineers to the concept of a practical steam-powered machine. The question of whether the Pneumatica represents the full extent of Heron's investigation of steam power, or whether he conducted additional experiments and built additional devices that were not described in the surviving text, is one that cannot be answered from the available evidence. The Pneumatica is a published text intended for a general audience, and it may not include all of the experimental work that Heron conducted in his workshop. The possibility that Heron built larger or more powerful steam devices that were not described in the Pneumatica cannot be excluded, though the absence of any reference to such devices in the surviving literature suggests that, if they existed, they were not widely known or widely discussed. The core problem with the Aeolipile is not that it did not work. It worked. The sphere spun, the steam escaped, the reaction force drove the rotation. The basic principle of steam power was demonstrated in a workshop in Alexandria 2,000 years ago, and the demonstration was successful. The core problem is that the demonstration was not followed by development, that the principle was not applied to practical work, and that the enormous potential of steam power was left unrealized for 17 centuries. The failure to develop the Aeolipile into a practical steam engine is not a simple story with a single cause. It is a complex story with multiple causes, each of which contributed to the outcome, and each of which reflects a specific aspect of the economic, social, intellectual, and technological conditions of the ancient world. The identification and the evaluation of these causes has been one of the most active areas of research in the history of technology, and the debate has produced a rich body of scholarship that illuminates not only the specific question of the Aeolipile, but also the broader question of what determines whether a technological discovery is developed into a transformative technology. The first and most frequently cited cause is the technological gap between the Aeolipile and a practical steam engine. The Aeolipile, as Heron built it, was a toy, a demonstration device that produced a small amount of rotational energy, but that was not capable of performing useful work. The development of the Aeolipile into a practical steam engine would have required the solution of a series of engineering problems that were beyond the capabilities of ancient technology, or that would have required a level of development effort that the ancient world was not prepared to invest. But here is the problem. The specific engineering challenges that would have needed to be overcome to develop the Aeolipile into a practical steam engine are substantial. The most fundamental challenge is the efficiency of the device. The Aeolipile, which uses reaction nozzles to convert steam into rotational motion, is inherently inefficient because the nozzles do not expand the steam efficiently, and because the reaction force is applied at a single point on the circumference of the sphere rather than being distributed over a larger surface area. The development of a more efficient steam engine would have required the replacement of the reaction nozzles with a piston and cylinder mechanism in which the pressure of the steam is applied to a piston that moves within a cylinder, converting the pressure energy of the steam into the mechanical energy of the piston's motion. The piston and cylinder mechanism, while it was known in the ancient world in the form of the force pump that was invented by Ctesibius, was never adapted for use as a steam-driven prime mover. The adaptation would have required the development of a cylinder that was large enough to produce useful power, a piston that fitted tightly enough within the cylinder to prevent the leakage of steam, and a valve mechanism that controlled the admission and the exhaust of steam to and from the cylinder. Each of these requirements posed engineering challenges that, while not insurmountable, would have required a sustained program of development that was not undertaken. The materials limitations of the ancient world are another factor that would have constrained the development of a practical steam engine. The operation of a steam engine at useful power levels requires the containment of steam at pressures that are significantly higher than atmospheric pressure, and the materials that are needed to contain high-pressure steam, specifically metals that are strong enough to resist the pressure without deforming or rupturing, were not readily available in the ancient world. The bronze and the iron that were available to the ancient engineers were adequate for the low pressures of the Aeolipile, but they would have been inadequate for the higher pressures that a practical steam engine would require. The development of the iron and steel alloys that could withstand the pressures of a practical steam engine required advances in metallurgy that were not achieved until the 17th and 18th centuries. The sealing of the moving parts of a steam engine, particularly the piston-cylinder interface, is another engineering challenge that would have been difficult to overcome with ancient materials. The piston must fit tightly within the cylinder to prevent the leakage of steam, which would reduce the efficiency and the power output of the engine. In the modern steam engine, the seal between the piston and the cylinder is achieved through precision machining of the cylinder bore and through the use of packing materials such as greased hemp or metallic rings that fill the gap between the piston and the cylinder. The precision machining that is needed to produce a cylinder with a sufficiently uniform bore was beyond the capabilities of ancient metalworking, and the packing materials that are used in modern steam engines, while they are simple in principle, required a level of development that the ancient world did not undertake. And it gets worse. The fuel supply for a steam engine is another constraint that would have limited its development in the ancient world. The operation of a steam engine requires a continuous supply of fuel to boil the water and to produce the steam, and the fuel that was available in the ancient Mediterranean world was primarily wood and charcoal. The consumption of fuel by a steam engine is substantial, and the operation of a steam engine over extended periods would have required a supply chain for fuel that would have been difficult and expensive to maintain using the transportation technology of the ancient world. The coal that powered the steam engines of the Industrial Revolution was available in the ancient world, particularly in Britain, but it was not extensively exploited until the medieval period, and its use as a fuel for steam engines was a development of the 17th and 18th centuries. The second major cause of the failure to develop the steam engine is the economic structure of the ancient world, which provided little incentive for the development of labor-saving technology. The economy of the ancient Mediterranean world was based, to a significant degree, on the labor of slaves, who provided the human power that drove agriculture, manufacturing, construction, and transportation. The availability of cheap slave labor reduced the economic incentive to develop mechanical alternatives to human labor because the cost of slave labor was low enough that the investment in the development and the deployment of a steam engine would not have been justified by the savings in labour costs. The slavery hypothesis, which has been the subject of extensive debate among economic historians, is controversial because it implies a direct causal relationship between the institution of slavery and the failure to develop labour-saving technology, a relationship that is difficult to establish with certainty. The critics of the slavery hypothesis have pointed out that slavery was not universal in the ancient world, that free labour was also widely used, and that the economic conditions that would have favoured the development of labour-saving technology varied widely across the ancient world. The critics have also pointed out that the medieval and early modern periods, which also relied on coerced labour in the form of serfdom and indentured servitude, did develop labour-saving technologies, including the watermill, the windmill, and the mechanical clock, suggesting that the relationship between coerced labour and technological stagnation is not as straightforward as the slavery hypothesis implies. The third major cause is the intellectual culture of the ancient world, which drew a sharp distinction between theoretical knowledge and practical application, between the life of the mind and the work of the hands, between the philosopher and the craftsman. The Greek intellectual tradition, which was the dominant intellectual tradition of the Hellenistic world, valued theoretical knowledge, the knowledge of principles and of causes, more highly than practical knowledge, the knowledge of techniques and of applications. The philosopher, who pursued knowledge for its own sake, was accorded a higher social status than the craftsman, who applied knowledge to practical purposes, and the intellectual prestige of theoretical inquiry was greater than the practical utility of applied engineering. This intellectual hierarchy, which was articulated by Aristotle and which was reinforced by the social structure of the ancient world, had consequences for the development of technology. The engineers and the inventors of the ancient world, who were typically of lower social status than the philosophers and the mathematicians, received less recognition, less patronage, and less institutional support than their more theoretical colleagues. The development of practical technology, while it was not entirely neglected, was not a priority of the intellectual establishment, and the resources that were devoted to technological development were a fraction of the resources that were devoted to theoretical inquiry. Heron himself occupied an ambiguous position within this intellectual hierarchy. He was both a mathematician and an engineer, a scholar who wrote treatises on geometry and on measurement, and who also designed and built mechanical devices. His willingness to engage with both the theoretical and the practical aspects of knowledge was unusual in the ancient world, and it may reflect the specific intellectual culture of Alexandria, which was more practically oriented than the philosophical schools of Athens, and which valued the application of knowledge to practical problems more highly than the Athenian tradition did. The question of whether Heron recognized the potential of the Aeolipile as a power source, and whether he would have been motivated to develop it if he had, is one that cannot be answered from the surviving evidence. Heron's description of the Aeolipile in the Pneumatica does not suggest that he regarded it as more than a demonstration of the motive power of steam, and his treatment of the device in the context of the other devices in the treatise suggests that he viewed it as one of many interesting mechanical curiosities, rather than as a potentially transformative technology. The concept of labour-saving technology, which is central to the modern understanding of the steam engine's significance, may not have been part of Heron's intellectual framework because the ancient world did not share the modern assumption that the reduction of human labour is a desirable social goal. The fourth major cause is the absence of the supporting technologies that would have been needed to develop the Aeolipile into a practical steam engine. The development of the steam engine in the 17th and 18th centuries was not a single invention, but a system of interdependent innovations, each of which depended on the others, and each of which was necessary for the practical functioning of the engine. The boiler, the piston, the cylinder, the condenser, the valve mechanism, the governor, and the flywheel are all components of the steam engine system, and the development of each component required specific materials, specific manufacturing techniques and specific engineering knowledge that were not available in the ancient world. The concept of technological clustering, the phenomenon in which multiple interdependent technologies must be developed simultaneously for any one of them to be useful, is relevant to the Aeolipile story. The Aeolipile by itself was not useful because it lacked the supporting technologies that would have been needed to convert its rotational energy into practical work. The development of those supporting technologies would have required a sustained program of research and development that was not undertaken, partly because the economic and social conditions of the ancient world did not provide the incentive for such a program, and partly because the intellectual culture of the ancient world did not prioritize the application of our scientific knowledge to practical problems. But here is what makes this truly terrifying. The failure to develop the steam engine was not inevitable. The engineering challenges, while substantial, were not insurmountable. The economic incentives, while they were weak, were not absent. The intellectual culture, while it devalued practical application, did not prohibit it. The failure to develop the steam engine was the result of a specific combination of conditions that, taken together, made the development unlikely, but not impossible. A different combination of conditions, a different economic structure, a different intellectual culture, a different set of social priorities might have produced a different outcome, and the history of human civilization might have been radically different. The question of whether the intellectual culture of the ancient world was a significant barrier to the development of the steam engine has been debated extensively by historians of science and technology, with different scholars reaching different conclusions depending on their interpretation of the ancient sources and their assumptions about the relationship between intellectual culture and technological development. The most influential statement of the view that the ancient intellectual culture was hostile to practical technology is found in the writings of the ancient sources themselves. Plutarch, writing in the 1st century of the Common Era, described how Archimedes, the greatest engineer of the ancient world, was reluctant to publish his practical inventions because he considered them to be unworthy of philosophical attention. According to Plutarch, Archimedes regarded his engineering work as a lesser activity that was beneath the dignity of a philosopher, and that distracted from the more important pursuit of pure mathematics. Plutarch's account, if accurate, suggests that even the most accomplished ancient engineers internalized the intellectual hierarchy that valued theory over practice, and that regarded the application of knowledge to practical problems as a lesser activity than the pursuit of knowledge for its own sake. The critics of the intellectual culture hypothesis have pointed out that Plutarch's account is a literary construction that may not accurately reflect Archimedes' own views, and that the ancient sources provide numerous examples of engineers and inventors who were celebrated for their practical achievements, including Ctesibius, who was praised for his hydraulic inventions, and Heron himself, whose practical treatises were widely read and widely admired. The critics have also pointed out that the intellectual culture of the ancient world was not monolithic, that it varied across time and across regions, and that the specific intellectual culture of Alexandria, which was more practically oriented than the philosophical culture of Athens, may have been more receptive to the development of practical technology than the Athenian culture that Plutarch described. The question of whether a different intellectual culture, one that valued practical application more highly and that provided greater prestige and greater support for applied engineering, could have produced the development of the steam engine, is one that is impossible to answer with certainty, but that is worth considering. The intellectual culture of early modern England, which valued useful knowledge and which celebrated the practical achievements of engineers and inventors, was clearly a factor in the development of the steam engine, and the absence of a similar culture in the ancient world was, at minimum, a contributing factor in the failure to develop the steam engine. The specific social status of engineers in the ancient world is another factor that may have influenced the development of technology. The ancient engineers were typically of lower social status than the philosophers and the mathematicians, and their work was regarded as less prestigious and less intellectually important. The social status of the engineer influenced the amount of patronage and institutional support that was available for engineering development, and the lower status of the engineer meant that less resources were devoted to the development of practical technology than to the pursuit of theoretical knowledge. The social elevation of the engineer in the early modern period, when engineers such as Watt, Newcomen, and Smeaton were celebrated as heroes of the Industrial Revolution, was a significant change from the ancient pattern, and it contributed to the acceleration of technological development that characterized the modern era. The analysis of the specific thermal and mechanical performance of the Aeolipile has been conducted by modern engineers using the tools of thermodynamic analysis and computational fluid dynamics. The thermodynamic analysis, which models the conversion of heat energy into mechanical work in the Aeolipile, has revealed that the fundamental limitation of the device is the low pressure at which it operates. The Aeolipile operates at approximately atmospheric pressure, with the steam pressure inside the sphere being only slightly above atmospheric pressure, and the energy that can be extracted from the steam at this low pressure is a tiny fraction of the total energy content of the steam. The development of a more efficient steam engine would have required the use of significantly higher steam pressures, which in turn would have required the development of a boiler that could contain the higher pressures without rupturing. The computational fluid dynamics analysis, which models the flow of steam through the nozzles of the Aeolipile and the forces that the steam jets exert on the sphere, has confirmed that the reaction nozzles are inherently inefficient as a mechanism for converting steam energy into mechanical work. The nozzles, which are simple bent tubes, do not expand the steam efficiently, and the supersonic expansion that occurs at the nozzle exit produces shock waves that dissipate a significant fraction of the steam's kinetic energy. The design of more efficient nozzles, such as the convergent-divergent nozzle that was developed by Gustave de Laval in the late 19th century, would have significantly improved the efficiency of the Aeolipile. But the principles of nozzle design were not understood in the ancient world and would not have been accessible to the Alexandrian engineers. The question of whether the Aeolipile could have been improved through empirical experimentation without the theoretical understanding of thermodynamics and fluid dynamics that was developed in the 18th and 19th centuries is one that has been considered by historians of technology. The answer is that some improvements could probably have been achieved through trial and error, such as the use of larger nozzles, the use of higher steam pressures achieved by sealing the boiler more tightly, and the use of a more efficient nozzle shape discovered through experimentation. But the fundamental improvement that would have been needed to convert the Aeolipile into a practical power source, the replacement of the reaction nozzles with a piston and cylinder mechanism, was not an improvement that could be achieved through empirical experimentation alone. It required a fundamental reconceptualization of the device, from a reaction turbine to a reciprocating engine. That was a conceptual leap rather than an incremental improvement. The role of friction in limiting the performance of the Aeolipile is another factor that has been investigated by modern engineers. The friction at the pivot points where the sphere is mounted and the air resistance on the spinning sphere both dissipate energy and reduce the power output of the device. The ancient engineers had limited means of reducing friction because the bearing technology of the ancient world was primitive compared to the roller bearings and the ball bearings that are used in modern machinery. The development of improved bearing technology would have increased the efficiency of the Aeolipile, but would not have addressed the fundamental limitations of the reaction nozzle design. The broader question of what the Aeolipile tells us about the nature of invention and the conditions that foster or hinder it has been explored by scholars of the history and the philosophy of technology. The Aeolipile is a case study in what the historian of technology, Abbott Payson Usher, called acts of insight, the specific creative moments in which an inventor perceives a new relationship between existing elements and combines them in a new way. Heron's insight, in the case of the Aeolipile, was the recognition that the escape of steam through a bent nozzle would produce a force that could cause a sphere to rotate. The insight was genuine and original, and it produced a device that demonstrated a new principle of mechanical action. But the insight was limited. It did not extend to the recognition that the principle could be applied to the performance of useful work on a larger scale. Or if Heron did recognize this possibility, he did not pursue it. The question of why Heron's insight was limited, why he recognized the reaction principle but did not apply it to practical work, is one that cannot be answered with certainty, but that can be illuminated by the analysis of the intellectual and the cultural context in which he worked. The ancient intellectual tradition, as we have discussed, drew a distinction between the theoretical understanding of principles and the practical application of principles, and it valued the former more highly than the latter. In this context, the demonstration of the principle of steam power in the Aeolipile may have been seen as a sufficient achievement, a contribution to the understanding of natural phenomena that did not need to be followed by the development of a practical application. The demonstration was the point, not the application. The contrast between this ancient attitude and the modern attitude toward technological innovation is stark. In the modern world, the demonstration of a new principle is typically seen as the beginning of a development process rather than as an end in itself, and the value of a discovery is measured not only by its intellectual significance, but also by its practical applications. The modern innovation system, which includes research universities, corporate research laboratories, venture capital firms, and government funding agencies, is designed to convert discoveries into technologies as efficiently and as rapidly as possible, and the social status and the economic rewards that accrue to successful innovators provide a powerful incentive for the development of practical applications. The ancient world lacked this innovation system, and the absence of the system was as significant a barrier to the development of steam power as the absence of the specific materials and the specific manufacturing techniques that would have been needed. The concept of adjacent possibilities, which was developed by the biologist Stuart Kaufman, and which has been applied to the history of technology by the writer Stephen Johnson, provides another useful framework for understanding the Aeolipile story. The concept refers to the set of innovations that are possible at any given time, given the existing stock of knowledge, techniques, and materials. The steam engine was not within the adjacent possible of the ancient world, because the development of the steam engine required innovations in metallurgy, in manufacturing, and in energy supply that were themselves not within the adjacent possible of the ancient world. The Aeolipile was at the boundary of the adjacent possible, a demonstration of a principle that could not be developed further without innovations that were themselves beyond the reach of the ancient world. The concept of adjacent possibilities helps to explain why the development of the steam engine required 17 centuries rather than 17 years. Each step in the development of the steam engine, from the Aeolipile to the blast furnace, to the boring mill, to the atmospheric engine, to the separate condenser, required the prior development of the innovations that made it possible, and each of those innovations required its own set of prior developments. The chain of dependencies that linked the Aeolipile to the modern steam engine was long and complex, and the closure of each link in the chain required the specific conditions that were present at the specific time and place where the innovation occurred. The development of the steam engine was not a single event, but a process that unfolded over 17 centuries, and the pace of the process was determined by the rate at which the links in the chain of dependencies were closed. The question of whether slave labor was the primary barrier to the development of labor-saving technology in the ancient world has been one of the most contentious debates in the economic history of the ancient world, and the Aeolipile story provides a specific case study that can be used to evaluate the competing arguments. The proponents of the slavery hypothesis argue that the availability of cheap slave labor in the Greco-Roman world reduced the economic incentive to develop mechanical alternatives to human labor, and that this reduced incentive was the primary reason why the Aeolipile was not developed into a practical steam engine. The strongest version of the slavery hypothesis was articulated by the ancient historian Moses Finley, who argued that the ancient world's reliance on slave labor created an economic structure in which the development of labor-saving technology was not only unnecessary but actually undesirable, because it would have displaced the slave labor force that was the foundation of the ancient economy. Finley's argument was influential and was widely accepted for several decades, but it has been challenged by subsequent scholars who have pointed to evidence that the ancient world did develop labor-saving technologies in specific contexts, and that the relationship between slavery and technological development was more complex than Finley's argument implied. The economic historian Kevin Green has argued that the ancient world's failure to develop the steam engine was not primarily the result of the availability of slave labor, but of the specific engineering challenges that we have described, combined with the absence of the specific economic demand that drove the development of the steam engine in the early modern period. Green has pointed to the development of the water mill, the screw press, and the Vitruvian crane as evidence that the ancient world was capable of developing labor-saving technologies when the economic conditions favored their development, and he has argued that the failure to develop the steam engine was a specific outcome that was influenced by specific factors rather than a general consequence of the ancient economic structure. The economic analysis of the ancient labor market provides additional context for evaluating the slavery hypothesis. The cost of slave labor in the ancient world varied widely depending on the specific time, place, and type of work, and the assumption that slave labor was uniformly cheap is an oversimplification. In some contexts, particularly in the large-scale mining and construction projects that were the primary employers of slave labor, the cost of acquiring, maintaining, and supervising a large slave workforce was substantial, and the economic advantages of a mechanical alternative might have been significant. In other contexts, particularly in the domestic and agricultural settings where most slaves were employed, the cost of slave labor was relatively low, and the economic advantage of a mechanical alternative would have been minimal. The question of whether the ancient world would have developed the steam engine if slavery had not existed is a counterfactual that is impossible to answer with certainty, because the social and the economic structure of the ancient world without slavery would have been so different from the actual structure that the consequences for technological development are unpredictable. The abolition of slavery would have increased the cost of labor, which would have increased the economic incentive to develop labor-saving technology, but it would also have reduced the wealth of the elite, which would have reduced the resources available for the patronage of engineering and for the investment in technological development. The net effect of these opposing forces on the development of the steam engine is impossible to determine, and the slavery hypothesis, while it is a plausible contributing factor, cannot be identified as the sole or even the primary cause of the failure to develop the steam engine. The specific question of whether the Aeolipile could have been connected to a practical load, such as a millstone or a water pump, without the development of a piston and cylinder mechanism, is one that has been considered by engineers who have analysed the mechanical properties of the device. The Aeolipile produces rotational motion, which is the type of motion that is needed to drive a millstone or a generator, and the question is whether the torque and the speed of the rotation are sufficient to perform useful work. The analysis has shown that the torque produced by the Aeolipile is very low because the reaction force of the steam jets is small and because the force is applied at the circumference of a small sphere. The low torque means that the Aeolipile cannot drive any load that requires significant force, such as a millstone or a pump. The speed of rotation is relatively high, several hundred to over 1,000 revolutions per minute, but the combination of high speed and low torque produces only a small amount of power, insufficient for any practical application. The development of a gear reduction system that would convert the high speed and low torque of the Aeolipile into the low speed and high torque that would be needed to drive a practical load would have been one approach to making the device useful. The Alexandrian engineers were familiar with gear systems, as demonstrated by the Antikythera mechanism and by the gear trains that Heron described in his treatises, and the development of a gear reduction system for the Aeolipile would have been within their capabilities. However, the gear reduction would not have increased the power output of the device, which is determined by the efficiency of the conversion of steam energy into mechanical work, and the low power output of the Aeolipile would have remained a fundamental limitation, even with a gear reduction system. The alternative approach of increasing the power output of the Aeolipile by increasing the size of the sphere, the pressure of the steam, or the flow rate through the nozzles has been analysed by engineers who have calculated the performance of scaled-up versions of the device. The analysis has shown that increasing the size of the sphere increases the power output but also increases the friction and the inertia, reducing the net gain. Increasing the pressure of the steam increases the power output significantly, but requires a stronger boiler and stronger pivots that can withstand the higher pressure, requirements that would have been difficult to meet with ancient materials. Increasing the flow rate through the nozzles increases the power output, but also increases the consumption of fuel and water, requiring a larger boiler and a larger fuel supply. The conclusion of the engineering analysis is that the development of a useful power source from the Aeolipile principle would have required not merely the scaling up of the existing device, but a fundamental redesign that replaced the reaction nozzles with a more efficient energy conversion mechanism. The specific redesign that would have been most effective, the replacement of the nozzles with a piston and cylinder mechanism, was the same redesign that was eventually implemented in the development of the modern steam engine, and the question of whether the Alexandrian engineers could have made this redesign is the central engineering question of the Aeolipile story. The answer, as we have discussed, is that the redesign was theoretically possible, but practically very difficult, because it required specific materials, specific manufacturing techniques, and specific engineering concepts that were at the outer limits of what the ancient world could provide. The development of the piston and cylinder steam engine required not only the concept of using steam to drive a piston, but also the development of a cylinder that could be bored to a uniform diameter, a piston that could be fitted with packing materials to prevent steam leakage, a valve mechanism that could control the timing of the steam admission and exhaust, and a connecting rod and crank mechanism that could convert the reciprocating motion of the piston into the rotary motion of a wheel. Each of these components required specific engineering innovations that were themselves dependent on prior innovations in metallurgy, in manufacturing, and in mechanical design. The dependency chain that connects the Aeolipile to the piston and cylinder steam engine is long and complex, with each link in the chain requiring the prior development of the preceding link. The boiler requires strong iron. The strong iron requires the blast furnace. The blast furnace requires coke or charcoal in large quantities. The boring of a uniform cylinder requires a boring mill. The boring mill requires a precision lathe. The precision lathe requires hardened steel tools. The hardened steel requires specific metallurgical knowledge. The valve mechanism requires precision casting and fitting. The piston rings require specific materials knowledge. Each requirement leads to another requirement, and the chain of requirements extends deep into the specific technological infrastructure of the civilization that undertakes the development. The concept of the minimum viable technology cluster, the minimum set of supporting technologies that must be present for a specific target technology to be developed, is useful for understanding the Aeolipile story. The minimum viable technology cluster for the piston and cylinder steam engine includes the blast furnace, the boring mill, the precision casting of iron, the development of packing materials, the development of valve mechanisms, and the availability of a cheap and abundant fuel source. The ancient world possessed none of these supporting technologies, and the development of each of them required its own set of supporting conditions that were not present in the ancient world. The technology cluster for the steam engine was simply too large and too complex to be developed in the conditions that prevailed in the ancient world, and the failure to develop the steam engine was the inevitable consequence of the mismatch between the size of the required technology cluster and the technological capabilities of the ancient world. The investigation of how ancient societies made decisions about which technologies to invest in and which to ignore provides additional context for the Aeolipile story. The ancient societies, like modern societies, faced choices about how to allocate their limited resources among competing demands, and the specific choices that they made reflected the specific values, the specific priorities, and the specific circumstances that characterized each society. The decision not to invest in the development of the steam engine, which may never have been a conscious decision at all, but rather the absence of a decision, reflects the specific priorities of the ancient world, which favored military technology, agricultural technology, and monumental construction over the development of new power sources. The Roman Empire, which controlled much of the Mediterranean world during the period when the Aeolipile was built, invested enormous resources in the development of military technology, including siege engines, warships, and fortification systems, and in the development of infrastructure, including roads, aqueducts, and harbours. The investment in these technologies produced tangible benefits for the empire, enhancing its military power and its economic prosperity, and the Roman authorities had strong incentives to continue these investments. The investment in the development of new power sources, which would have required a long-term commitment with uncertain returns, was less attractive to the Roman authorities than the investment in technologies that produced immediate and tangible benefits, and the development of the steam engine was not pursued because it was not a priority. The question of whether a different set of priorities, one that valued long-term technological development more highly than immediate military and economic returns, could have produced the development of the steam engine in the ancient world, is another counterfactual that is impossible to answer with certainty. The Ptolemaic rulers of Egypt, who were the patrons of the Alexandrian school, did invest in long-term intellectual projects, including the library and the Maution, that produced benefits that extended far beyond the immediate lifetimes of the rulers themselves. The possibility that a similar long-term investment in technological development could have produced the steam engine is not impossible, but it would have required a degree of foresight and a willingness to accept uncertainty that was exceptional even by the standards of the Ptolemaic court. The question of whether there were moments in the ancient world when the conditions for steam engine development were closer to being met than at other times is one that has been explored by historians. The late Roman Empire, with its growing reliance on water mills and its increasing military demand for siege engines and naval vessels, may have represented a period when the economic incentive for mechanical power was increasing. The specific conditions of the late Roman mining industry, which faced growing challenges of water management as mines were deepened, may have created localized demand for pumping technology. But even in these periods of heightened demand, the technological infrastructure that would have been needed for the development of a practical steam engine remained beyond the reach of the ancient engineers, and the conditions, while they were closer to being sufficient, still fell short of the threshold that the development required. The investigation of the Aeolipile and the broader question of why the ancient world did not develop the steam engine has been conducted by researchers from a remarkable range of disciplines, including the history of technology, economics, sociology, classical studies, mechanical engineering, and the philosophy of science. The investigation has produced a body of scholarship that is both extensive and contentious, with different researchers reaching different conclusions based on different assumptions, different methods, and different evaluations of the available evidence. The first major track of investigation has been the reconstruction and the testing of the Aeolipile itself, aimed at determining the specific performance characteristics of the device and at evaluating the engineering challenges that would have been involved in developing it into a practical steam engine. Several researchers and engineers have built replicas of the Aeolipile based on Heron's description, and they have measured the rotational speed, the power output, and the efficiency of the replicas under various operating conditions. The reconstructions have confirmed that the Aeolipile works as Heron described, producing a rotational motion that is driven by the reaction force of the escaping steam. The rotational speed of the replica Aeolipiles has been measured at several hundred to over 1,000 revolutions per minute, depending on the size of the sphere, the diameter of the nozzles, and the steam pressure. The power output, as we have noted, is small, typically in the range of 1 to 2 watts, and the efficiency is low, typically less than 1%. The reconstructions have therefore confirmed that the Aeolipile is a functioning demonstration of the reaction engine principle, but they have also confirmed that the device, as described by Heron, is far too inefficient and far too low-powered to be useful as a practical power source. The question of whether the Aeolipile could have been scaled up to produce useful power has been investigated by engineers who have analysed the thermodynamic and the mechanical performance of the device and who have identified the specific modifications that would be needed to increase its power output and its efficiency. The most important modification would be the replacement of the reaction nozzles with a piston and cylinder mechanism, which would increase the efficiency of the conversion of steam pressure into mechanical work by a factor of 10 or more. The addition of a condenser, which would cool the exhausted steam and create a partial vacuum that would increase the pressure difference across the piston, would further increase the efficiency and the power output, and the use of higher steam pressures, achieved by heating the water to higher temperatures in a sealed boiler, would increase the energy content of the steam and thereby increase the power output of the engine. The engineering analysis has concluded that the development of a practical steam engine from the Aeolipile would have required approximately the same series of innovations that were actually required for the development of the modern steam engine in the 17th and 18th centuries. The development of a boiler capable of generating steam at pressures above atmospheric, the development of a piston and cylinder mechanism capable of converting steam pressure into mechanical work, the development of a condenser capable of recovering the waste heat, and the development of a valve mechanism capable of controlling the admission and the exhaust of steam. Each of these innovations required specific materials, specific manufacturing techniques, and specific engineering knowledge that were at the outer limits of what the ancient world could provide. The second major track of investigation has been the study of the other mechanical devices described by Heron and by his predecessors, aimed at determining the overall state of Alexandrian mechanical engineering, and at evaluating whether the Alexandrian engineers possessed the specific capabilities that would have been needed to develop the Aeolipile into a practical steam engine. The study of the Alexandrian mechanical tradition has revealed a level of engineering sophistication that is impressive by any standard, with devices that demonstrate a command of pneumatic principles, of hydraulic principles, and of mechanical linkages that is consistent with a tradition that was capable of significant engineering development. The specific devices described by Heron that are most relevant to the question of steam engine development include the force pump of Ctesibius, which demonstrates the piston and cylinder principle that is the foundation of the reciprocating steam engine, the wind-powered organ, which demonstrates the conversion of the kinetic energy of a flowing gas into mechanical work, and the automatic theatre, which demonstrates the use of a stored energy source, a descending weight, to drive a complex sequence of mechanical actions through a system of ropes, pulleys, and cams. Each of these devices demonstrates a specific engineering principle that is relevant to the development of a steam engine, and the fact that the Alexandrian engineers possessed these capabilities in isolation but did not combine them into a steam engine is one of the most tantalizing aspects of the Aeolipile story. The automatic doors that Heron described in the Pneumatica deserve particular attention because they demonstrate the use of steam as a motive force for a practical application, albeit a ceremonial one rather than an industrial one. The device worked by using the heat of a fire on the temple altar to boil water in a sealed vessel beneath the altar, generating steam that displaced water from the vessel into a hanging bucket. The weight of the water in the bucket pulled on ropes that were connected to the hinges of the temple doors, causing the doors to open. When the fire was extinguished, the steam condensed, creating a partial vacuum that drew the water back from the bucket into the vessel, and the doors closed as the weight of the empty bucket was lifted by a counterweight. The automatic temple doors are significant because they demonstrate that Heron understood the concept of using steam to perform mechanical work, the same concept that is the foundation of the steam engine. The device converts the heat of the fire into the kinetic energy of the opening doors, using steam as the intermediate energy carrier. The device is, in a fundamental sense, a steam engine, albeit one that performs a single slow intermittent action rather than a continuous rapid, repetitive one. The existence of the automatic temple doors demonstrates that the conceptual leap from the Aeolipile to a practical steam-powered device was not as large as it might appear, because Heron had already made the connection between steam and mechanical work in the design of the temple doors. The third major track of investigation has been the economic analysis of the ancient world, aimed at determining whether the economic conditions of the Greco-Roman world would have supported the development and the deployment of a steam engine if the engineering challenges had been overcome. The economic analysis has produced a range of conclusions, from the view that the ancient economy was too primitive and too reliant on slave labor to support the development of labor-saving technology, to the view that the ancient economy was sufficiently dynamic and sufficiently responsive to economic incentives that the development of a steam engine would have been economically rational if it had been technically feasible. The economic historian Moses Finley, whose influential work The Ancient Economy was published in 1973, argued that the ancient economy was fundamentally different from the modern economy, and that the ancient world lacked the specific economic institutions, the capital markets, the entrepreneurial culture, and the concept of labor productivity that would have been needed to support the development of labor-saving technology. Finley's view, which was widely influential in the decades following the publication of his book, implied that the failure to develop the steam engine was an inevitable consequence of the economic structure of the ancient world, and that no amount of engineering capability could have overcome the economic barriers. The critics of Finley's view, including the economic historian Kevin Green, have argued that the ancient economy was more dynamic and more responsive to economic incentives than Finley acknowledged, and that the ancient world did develop labor-saving technologies, including the water mill, the screw press, and the crane, when the economic conditions favored their development. Green has argued that the failure to develop the steam engine was not an inevitable consequence of the economic structure of the ancient world, but a specific outcome that was influenced by specific factors, including the engineering challenges that we have discussed, the availability of slave labor, and the intellectual culture that devalued practical technology. The fourth major track of investigation has been the comparative analysis of the Alexandrian Aeolipile and the early modern steam engines that were developed in the 17th and 18th centuries, aimed at identifying the specific conditions that were present in the early modern period but absent in the ancient world that enabled the development of the steam engine. The comparative analysis has revealed that the early modern steam engine was developed in a specific economic, social, and intellectual context that was fundamentally different from the context of the ancient world, and that the specific differences between the two contexts provide the most compelling explanation for the failure to develop the steam engine in the ancient world. The most important difference between the ancient and the early modern contexts is the specific economic demand that drove the development of the early modern steam engine. The development of the steam engine in England in the late 17th and early 18th centuries was driven by a specific and urgent economic problem: the need to pump water from the coal mines that were being deepened to meet the growing demand for coal. The coal mines of England, which were the primary source of fuel for the heating of homes and for the smelting of iron, were being flooded by groundwater as they were dug deeper, and the existing technology for pumping water, which relied on human labor, animal labor, and the limited power of water-driven pumps, was inadequate for the volumes of water that needed to be removed. The development of the steam-driven pump, which was first achieved by Thomas Savery in 1698 and which was improved by Thomas Newcomen in 1712, was a direct response to this specific economic demand, and the revenue that the steam pump generated from the mining industry provided the economic incentive for the continued development and improvement of the technology. The ancient world had no equivalent economic demand. The ancient mining industry, while it was substantial, did not face the specific problem of groundwater flooding that drove the development of the steam pump in early modern England, because the ancient mines were typically shallower than the early modern mines, and because the water management technique that were available to the ancient miners, including drainage channels and bucket chains, were adequate for the volumes of water that needed to be removed. The absence of a specific and urgent demand for a new pumping technology meant that there was no economic incentive for the development of a steam-driven pump, and the enormous development effort that would have been required to convert the Aeolipile into a practical pumping engine was not justified by any identifiable economic return. The second important difference is the scientific culture of the early modern period, which valued the application of scientific knowledge to practical problems in a way that the ancient world did not. The scientific revolution of the 16th and 17th centuries, which produced the work of Galileo, of Newton, of Boyle, and of their many contemporaries, established a new intellectual framework in which the systematic investigation of natural phenomena was valued not only for its own sake, but also for the practical benefits that it could produce. The concept of useful knowledge, knowledge that could be applied to the improvement of agriculture, of manufacturing, of navigation, and of other practical activities, became a central value of the scientific culture of the early modern period, and the application of scientific knowledge to practical problems became a prestigious and a socially valued activity. The ancient world did not share this valuation of useful knowledge. The Greek intellectual tradition, which was the dominant intellectual tradition of the Hellenistic world, valued theoretical knowledge over practical application, and the social prestige of the philosopher was higher than the social prestige of the engineer. The application of scientific knowledge to practical problems was not despised, but it was not the primary purpose of scientific inquiry, and the scientists who applied their knowledge to practical problems, including Heron himself, occupied a lower rung of the intellectual hierarchy than the scientists who pursued knowledge for its own sake. The third important difference is the availability of specific materials and manufacturing techniques that were needed for the construction of a practical steam engine. The early modern steam engine was built from iron that was produced by the blast furnace, a smelting technology that was developed in the 15th century, and that produced iron in the large quantities and the specific forms that were needed for the construction of boilers, cylinders, and pistons. The precision machining that was needed to produce a cylinder with a sufficiently uniform bore was achieved using the boring mill, a machine tool that was developed in the 18th century specifically for the production of steam engine cylinders. The sealing of the piston within the cylinder was achieved using metallic piston rings and packing materials that were developed through a process of trial and error over the course of the 18th century. The ancient world lacked these specific materials and manufacturing capabilities. The iron that was available to the ancient engineers was bloomery iron, which was produced in small quantities and which was not suitable for the construction of large boilers and cylinders. The precision machining that was needed to produce a uniform cylinder bore was beyond the capabilities of ancient metalworking, which relied on hand tools and on the skill of the individual craftsman rather than on the precision of machine tools. And the sealing materials that would have been needed to prevent the leakage of steam around the piston were not available in the ancient world, at least not in the forms and the quantities that would have been needed for a practical steam engine. The cumulative effect of these differences, the absence of specific economic demand, the intellectual culture that devalued practical application, and the limitations of the available materials and manufacturing techniques provides a comprehensive explanation for the failure to develop the steam engine in the ancient world. The failure was not the result of any single factor, but of the convergence of multiple factors that, taken together, made the development of the steam engine virtually impossible in the conditions that prevailed in the ancient world. The numbers are striking when we compare the timeline of the Aeolipile with the timeline of the modern steam engine. Heron described the Aeolipile in approximately 62 of the Common Era. Thomas Savery patented the first practical steam-driven pump in 1698. Thomas Newcomen built the first practical atmospheric steam engine in 1712. James Watt patented his improved steam engine with a separate condenser in 1769. The interval between Heron's demonstration and Savery's pump is approximately 1636 years. The interval between Savery's pump and Watt's engine is approximately 71 years. The development of the steam engine, once it began, proceeded rapidly, with major improvements following one another at intervals of decades rather than centuries. But the interval between the discovery of the principle and the beginning of development was enormous, measured in millennia rather than in decades. The rapid pace of development once the process began, compared to the long stagnation before the process began, provides evidence for the importance of the supporting conditions that we have described. Once the conditions were right, once the economic demand existed, the social incentive was present, the intellectual culture was supportive, and the material capabilities were available, the development of the steam engine proceeded rapidly, with each improvement building on the previous one, and with the pace of improvement accelerating over time. The long stagnation before the development began was not the result of a lack of ingenuity or a lack of creativity. It was the result of the absence of the conditions that were needed to convert ingenuity and creativity into practical technology. The specific chain of innovations that led from the Aeolipile to the modern steam engine illustrates the concept of technological path dependence, the phenomenon in which the specific sequence of innovations that leads to a final outcome is determined by the specific conditions that existed at each step of the sequence, and in which the outcome would have been different if the conditions at any step had been different. The Aeolipile, which is a reaction turbine, was not the ancestor of the modern steam engine, which is a reciprocating piston engine. The modern steam engine evolved from the atmospheric engine of Newcomen, which was itself a development of the piston pump, and the turbine principle that the Aeolipile demonstrated was not incorporated into practical steam technology until the development of the steam turbine by Charles Parsons in 1884. The fifth major track of investigation has been the study of the transmission of the Aeolipile's description through the medieval period, aimed at tracing the path by which Heron's text was preserved, and at determining whether the knowledge of the Aeolipile influenced the development of steam technology in the early modern period. The Pneumatica was translated into Arabic in the 9th century by the scholars of the Islamic Golden Age, and the Arabic translation was subsequently used as the basis for Latin translations that were produced in the 12th and 13th centuries. The text was therefore available to the scholars of both the Islamic world and the medieval European world, though the degree to which it influenced the development of practical technology in either tradition is debated. The Islamic scholars who translated and studied the Pneumatica were interested primarily in the theoretical and the recreational aspects of the devices that Heron described, and they do not appear to have attempted to develop the Aeolipile or any of the other steam-driven devices into practical power sources. The Islamic world did develop a sophisticated tradition of mechanical engineering, producing a wide range of automata, water clocks, and other mechanical devices that were influenced by the Alexandrian tradition. But the development of steam power was not part of this tradition. The European scholars who encountered the Pneumatica through the Latin translations of the 12th and 13th centuries were similarly interested primarily in the theoretical and the recreational aspects of the devices, and the text does not appear to have directly stimulated the development of steam technology in the medieval period. The development of the steam engine in the 17th and 18th centuries was driven primarily by the practical demands of the mining industry and by the experimental investigations of natural philosophers such as Denis Papin, who developed the concept of the piston and cylinder steam engine in the 1680s, and by engineers such as Savory and Newcomen, who built the first practical steam engines in the late 17th and early 18th centuries. The question of whether Papin, Savory, or Newcomen were aware of Heron's description of the Aeolipile, and whether their work was influenced by it, is one that has been investigated by historians of technology. The evidence suggests that Papin was aware of the pneumatica and that he had read descriptions of the Aeolipile, but that his development of the piston and cylinder steam engine was primarily influenced by his own experimental investigations and by the work of his contemporaries, particularly the air pump experiments of Robert Boyle and Otto von Guericke. The direct influence of the Aeolipile on the development of the modern steam engine appears to have been minimal, with the modern engine being developed through an independent path of innovation that was driven by practical demands rather than by the study of ancient texts. The preservation of the pneumatica through the medieval period, while it did not directly contribute to the development of the steam engine, is nonetheless significant because it demonstrates the resilience of written knowledge and the importance of the manuscript tradition for the preservation of the intellectual heritage of the ancient world. The text of the pneumatica survived the fall of the Roman Empire, the Dark Ages of Western Europe, and the cultural disruptions of the medieval period, passing from Greek to Arabic to Latin through a chain of scribes and translators that extended over more than 1,000 years. The survival of the text is a testament to the dedication of the scholars and the scribes who copied and preserved it, and it is a reminder that the preservation of knowledge requires not only the initial creation of the text, but also the sustained effort of successive generations to copy, to translate, and to maintain the physical manuscripts in which the knowledge is recorded. The sixth major track of investigation has been the study of the cultural and philosophical contexts of technology in the ancient world, aimed at understanding the specific attitudes and values that influenced the ancient world's approach to technological development. The cultural context of technology is an important factor in the Aeolipile story, because the specific attitudes of the ancient world toward practical technology, toward manual labor, and toward the application of knowledge to practical problems influenced the resources and the social status that were available for technological development. The distinction between the liberal arts, which were considered worthy of a free man, and the mechanical arts, which were considered suitable only for slaves and craftsmen, was a fundamental feature of the ancient intellectual landscape that influenced the social status of engineers and the prestige of technological development. The liberal arts, which included grammar, rhetoric, logic, geometry, arithmetic, music, and astronomy, were valued as intellectual pursuits that developed the mind and that were appropriate for the educated elite. The mechanical arts, which included engineering, manufacturing, agriculture, and other practical activities, were valued for their utility, but were regarded as inferior to the liberal arts in intellectual prestige and in social status. This distinction, which was articulated by Aristotle and which was reinforced by the social structure of the Greco-Roman world, created an intellectual hierarchy in which the pursuit of theoretical knowledge was valued more highly than the development of practical technology. The engineers and the inventors of the ancient world, who were engaged in the mechanical arts, occupied a lower position in this hierarchy than the philosophers and the mathematicians, who were engaged in the liberal arts, and the social prestige and the institutional resources that were available for technological development were correspondingly lower. The question of how this intellectual hierarchy influenced the specific development of the Aeolipile is one that requires careful analysis. The hierarchy did not prevent the development of technology entirely, because the ancient world did develop a wide range of practical technologies, including the watermill, the screw press, the crane, the force pump, and many others. But the hierarchy may have limited the resources and the attention that were devoted to the development of technology, and it may have directed the energies of the most talented individuals away from engineering and toward the more prestigious pursuits of philosophy and mathematics. If Heron had been born in a society that valued engineering as highly as philosophy, would he have devoted more attention to the development of the Aeolipile as a practical power source? The question is unanswerable, but it is worth asking. The specific role of patronage in the development of technology in the ancient world is another factor that is relevant to the Aeolipile story. The development of technology in the ancient world, like the development of art and of learning, was dependent on the patronage of wealthy individuals and of the state, and the specific interests and the specific priorities of the patrons influenced the direction and the pace of technological development. The Ptolemaic rulers of Egypt, who were the primary patrons of the Alexandrian school, were interested in technologies that enhanced their military power, that improved their economic prosperity, and that demonstrated their cultural sophistication, and they provided funding for engineering projects that served these purposes. The development of the Aeolipile into a practical steam engine would have required sustained patronage over a period of years or decades, and the question of whether the Ptolemaic rulers would have been willing to invest the necessary resources in such a project, given the uncertain prospects of success and the availability of cheaper alternatives in the form of slave and animal labor, is one that the surviving historical evidence does not answer. The comparison between the ancient and the early modern approaches to the development of steam technology reveals a fundamental difference in the way that the two civilizations approached the relationship between science and technology. The ancient approach, as exemplified by Heron and the Alexandrian school, was primarily observational and demonstrative, focused on the identification and the demonstration of natural principles without the development of practical applications. The early modern approach, as exemplified by Savory, Newcomen, and Watts, was primarily practical and developmental, focused on the solution of specific problems and the development of specific applications, without necessarily understanding the theoretical principles that underlay them. The early modern engineers who developed the steam engine were not scientists in the modern sense. Savory was a military engineer, Newcomen was an ironmonger, Watt was an instrument maker. They were practical men who were driven by practical problems, and their approach to the development of the steam engine was empirical, based on trial and error rather than on theoretical analysis. The theoretical understanding of the thermodynamic principles that govern the operation of the steam engine was not developed until the work of Sadi Carnot in 1824, over a century after the development of the first practical steam engine. The development of the steam engine, therefore, proceeded in the opposite direction from the development of the Aeolipile. The Aeolipile began with a theoretical demonstration and failed to develop into a practical technology, while the steam engine began with a practical need and succeeded despite the absence of theoretical understanding. The comparison suggests that the practical, need-driven approach to technological development is more effective than the theoretical, knowledge-driven approach, at least in the specific context of the development of new power technologies. The ancient world had the knowledge but not the need, while the early modern world had the need but not the knowledge. And the early modern world succeeded where the ancient world failed. The lesson is that need, in the form of a specific economic demand that justifies the investment of resources in the development of a new technology, is a more powerful driver of technological development than knowledge, in the form of the theoretical understanding of the principles that underlie the technology. This conclusion, while it is supported by the specific example of the steam engine, should not be overgeneralized. The relationship between knowledge and need in technological development is complex, and there are many examples of technologies that were developed through a knowledge-driven approach, including the transistor, the laser, and the nuclear reactor that demonstrate that theoretical understanding can be a powerful driver of technological development when it is combined with the appropriate economic incentives and institutional support. The lesson of the Aeolipile is not that knowledge is irrelevant to technological development, but that knowledge alone is not sufficient, and that the conversion of knowledge into technology requires conditions that are not always present and that cannot always be created by the effort of individual inventors. The specific economic conditions that supported the development of the steam engine in early modern England have been studied in detail by economic historians who have identified a set of conditions that were unique to England in the 17th and 18th centuries, and that explain why the steam engine was developed there rather than in any other country. The most important of these conditions was the high cost of labour relative to the cost of energy, particularly coal, which created a strong economic incentive to develop labour-saving technologies that used coal as their energy source. England had abundant coal deposits that were easily accessible and that provided a cheap source of energy, and the cost of human labour in England was relatively high compared to other countries, creating a specific economic environment in which the substitution of mechanical energy for human labour was economically attractive. The ancient world had a different economic environment in which the cost of human labour, in the form of slave labour, was relatively low compared to the cost of fuel, which was primarily wood and charcoal. In this environment, the substitution of mechanical energy for human labour was not economically attractive because the cost of the fuel that would be needed to operate a steam engine was higher than the cost of the slave labour that the engine would replace. The economic calculus of the ancient world therefore favoured the continuation of the existing labour-based technology over the development of a new fuel-based technology, and that the steam engine was not developed because it would not have been economically competitive with the existing alternatives. The seventh major track of investigation has been the study of the specific environmental and resource conditions that influence the development of power technology in the ancient and the early modern worlds. The availability of specific energy resources, particularly wood, charcoal, and coal, influence the economic viability of different power technologies and shape the specific path of technological development that was followed in different regions and at different periods. The ancient Mediterranean world relied primarily on wood and charcoal as its energy sources, and the supply of these fuels was limited by the availability of forests and by the rate at which the forests could regenerate after harvesting. The deforestation that resulted from the demand for fuel, for construction, and for agriculture was a significant environmental problem in the ancient Mediterranean, and the increasing scarcity of wood and charcoal may have constrained the development of energy-intensive technologies, including the hypothetical development of a steam engine that would have required a continuous and substantial supply of fuel. The early modern world, by contrast, had access to coal, a fossil fuel that was far more energy-dense than wood or charcoal, and that was available in enormous quantities in specific geological formations, particularly in England, in Belgium, and in Germany. The availability of coal in England provided a specific advantage for the development of the steam engine because the steam engine could be fueled by the same coal that it was designed to extract from the mines, creating a self-reinforcing cycle of development in which the steam engine enabled the extraction of the fuel that powered the steam engine. The absence of an equivalent self-reinforcing cycle in the ancient world is another factor that helps to explain the failure to develop the steam engine. A steam engine fueled by wood or charcoal would have consumed its fuel at a rate that would have been difficult to sustain with the forestry practices of the ancient world, and the economic cost of the fuel would have been a significant barrier to the widespread deployment of the technology. The specific advantage of coal, which was cheaper, more energy-dense, and more abundant than wood or charcoal, was not available to the ancient engineers, and the absence of this advantage was another factor that made the development of the steam engine economically unviable in the ancient world. The study of the specific metallurgical capabilities that were available at different periods in the history of steam engine development has revealed a progression of capabilities that was closely connected to the progression of steam engine design. The early steam engines of Savory and Newcomen were built from cast iron that was produced by the blast furnace, a technology that was developed in Europe in the 15th century, and that was not available in the ancient world. The improved steam engines of Watt and his successors required wrought iron that was produced by the puddling process, a technology that was developed in the late 18th century. The high-pressure steam engines of the 19th century required steel that was produced by the Bessemer process, a technology that was developed in the 1850s. Each generation of steam engine required a specific metallurgical capability that was not available to the previous generation, and the progression of capabilities was a sequential process that could not have been compressed or accelerated. The eighth major track of investigation has been the analysis of the social networks and the institutional structures that supported technological innovation in the ancient and the early modern worlds, aimed at understanding why the ancient institutions, including the Mausian, failed to produce the sustained development effort that would have been needed to convert the Aeolipile into a practical steam engine, while the early modern institutions, including the Royal Society, the patent system, and the entrepreneurial networks of the British industrial districts, succeeded in producing the sustained development effort that led to the modern steam engine. The Mausian, which was the primary institutional home of the Alexandrian engineering tradition, was funded by the Ptolemaic state and was organized as a community of scholars who were provided with salaries, with housing, and with access to the library's collection. The scholars of the Mausian were free to pursue their research interests without the pressure of producing practical results, and the institution's primary purpose was the advancement of knowledge rather than the development of technology. The lack of pressure to produce practical results, while it may have been beneficial for the pursuit of pure knowledge, was a disadvantage for the development of practical technology because it removed the urgency and the economic incentive that are typically needed to drive a sustained development effort. The early modern institutions that supported the development of the steam engine were fundamentally different in their structure and in their purpose. The patent system, which was established in England in the early 17th century, provided inventors with a limited monopoly on their inventions, creating an economic incentive for the development of new technologies that was absent in the ancient world. The Royal Society and its continental equivalents, which were established in the mid-17th century, provided a forum for the exchange of scientific and technical information that facilitated the diffusion of new ideas and the collaboration of researchers across institutional boundaries. The entrepreneurial networks of the British industrial districts, which connected inventors, manufacturers, financiers, and customers in a web of relationships that facilitated the commercialization of new technologies, provided the organizational infrastructure that was needed to convert laboratory prototypes into commercial products. The comparison between the Mausian and the early modern innovation institutions reveals a fundamental difference in the relationship between the institutions and the society they served. The Mausian was insulated from the economic demands of the society, providing its scholars with the freedom to pursue knowledge without the pressure of producing practical results. The early modern institutions were embedded in the economic system of the society, responding to the economic demands of the market, and providing incentives for the development of technologies that met those demands. The insulation of the Mausian protected its scholars from economic pressure, but also isolated them from the economic signals that would have directed their energies toward the development of practically useful technologies. The embeddedness of the early modern institutions exposed their members to economic pressure, but also connected them to the economic signals that directed their energies toward the development of technologies that the market demanded. The lesson of the institutional comparison is that the development of practical technology requires institutions that are embedded in the economic system and that are responsive to the economic signals that indicate where the demand for new technologies is greatest. The Mausian, which was insulated from the economic system, produced theoretical knowledge and demonstrated new principles, but did not develop those principles into practical technologies. The early modern institutions, which were embedded in the economic system, responded to the specific economic demand for a new pumping technology and produced the steam engine within a few decades of the demand becoming urgent. The difference between the two outcomes is not a difference in the talent or the creativity of the individuals involved, but a difference in the institutions within which they worked, and in the incentive structures that guided their efforts. The ninth major track of investigation has been the philosophical analysis of the concept of technological potential, the idea that a specific technological capability exists in latent form within the knowledge and the capabilities of a society, and that it will be realized when the specific conditions for its development are present. The Aeolipile demonstrates that the potential for the steam engine existed in the ancient world in the form of the demonstrated principle of steam power and the engineering capabilities of the Alexandrian school, but that the potential was not realized because the conditions for its development were not present. The concept of technological potential is useful because it distinguishes between the capability to develop a technology and the actuality of developing it, and because it identifies the specific conditions that are needed to convert the capability into the actuality. The ancient world had the capability to develop the steam engine in the sense that the basic principle was known and the basic engineering skills were available, but the actuality of the development required conditions, economic, social, intellectual, and material, that were not present in the ancient world and that could not have been created by any single decision or any single investment. The distinction between capability and actuality is important because it prevents us from either overestimating or underestimating the technological achievements of the ancient world. The ancient world was capable of more than it actually achieved because many technologies that were within its capability were not developed, either because the conditions were not right or because the specific combination of factors that was needed for the development did not converge. At the same time, the ancient world was not capable of everything that the modern world has achieved, because some modern technologies require materials, manufacturing techniques, and theoretical knowledge that were genuinely beyond the reach of the ancient world, regardless of the conditions that prevailed. The Aeolipile sits at the boundary between what the ancient world was capable of and what it was not. The demonstration of the steam principle was within the capability of the ancient world, and it was achieved. The development of a practical steam engine was at the outer limits of what the ancient world was capable of, and it was not achieved. The boundary between the achievable and the unachievable is not a sharp line, but a gradual transition, and the Aeolipile is located in the zone of this transition, where the outcome depends critically on the specific conditions that prevail, and where a different set of conditions might have produced a different outcome. Everything we have discussed so far concerns the specific engineering challenges, the specific economic conditions, the specific intellectual culture, and the specific material limitations that prevented the development of the Aeolipile into a practical steam engine. These factors are important, and they provide a comprehensive explanation for the failure to develop the steam engine in the ancient world. But beneath these specific factors lies a deeper truth, a truth that concerns not just why the steam engine was not developed, but what the failure to develop it tells us about the nature of technological progress, the relationship between discovery and development, and the conditions that determine whether a discovery becomes a technology or remains a curiosity. The deeper truth is this: the discovery of a principle is not the same as the development of a technology. The Aeolipile demonstrated the principle of steam power. The discovery of the principle was necessary for the development of the technology, but it was not sufficient. The development of the technology required, in addition to the principle, a specific set of supporting conditions, economic, social, intellectual, and material, that were not present in the ancient world, but that were present in the early modern world. The failure to develop the steam engine was therefore not a failure of discovery. It was a failure of development, a failure that was caused not by the absence of knowledge, but by the absence of the conditions that were needed to convert knowledge into technology. This is not science fiction. This is a fundamental insight into the nature of technological progress, an insight that is as relevant to the modern world as it is to the ancient one. The modern world is full of discoveries that have not been developed into technologies, principles that have been demonstrated in laboratories, but that have not been converted into practical products, inventions that have been patented, but that have never been manufactured. The gap between discovery and development, the gap that the Aeolipile illustrates so dramatically, is a permanent feature of the technological landscape, and the factors that determine whether a discovery crosses the gap or falls into it are the same factors that determine the fate of the Aeolipile: the economic demand, the social incentive, the intellectual framework, and the material capability. Something is wrong with our assumption that technological progress is driven by discovery. The standard narrative of technological progress presents the history of technology as a story of discoveries, of eureka moments in which a new principle or a new technique is identified, and in which the application of the discovery to practical problems follows naturally and inevitably. The Aeolipile story demonstrates that this narrative is misleading because it conflates discovery with development, and because it ignores the specific conditions that are needed to convert a discovery into a technology. The discovery of the principle of steam power did not lead to the development of the steam engine for 17 centuries, not because the principle was forgotten, but because the conditions for its development were not present. The concept of the development gap, the distance between a discovery and its practical application, is useful for understanding the Aeolipile story and for understanding the broader history of technology. The development gap for the steam engine was enormous, measured not in years but in centuries, and the closure of the gap required not only the preservation of the original discovery, but also the development of a specific set of supporting conditions that did not exist when the discovery was made. The gap was not closed by a single genius or a single breakthrough. It was closed by the gradual accumulation of economic, social, intellectual, and material conditions that, taken together, created the environment in which the development of the steam engine was possible. The comparison between the fate of the Aeolipile and the fates of other ancient technologies provides additional perspective on the development gap. The Antikythera mechanism, which demonstrated the principle of gear-based mechanical computing, was not developed into a computing technology for over 1,000 years until the medieval development of the mechanical clock. The Roman concrete, which demonstrated the principle of pozzolanic hydraulic cement, was not redeveloped for approximately 1,500 years until the development of modern Portland cement. The Baghdad battery, which may have demonstrated the principle of electrochemistry, was not developed into an electrical technology, if indeed it was a battery at all, until Volta's invention of the voltaic pile in 1800. In each case, the discovery of a principle preceded the development of a technology by centuries or millennia, demonstrating that the development gap is not an anomaly of the Aeolipile story, but a recurring pattern in the history of technology. The question of whether the development of the steam engine could have been accelerated if the ancient world had invested the resources in a directed development program is a counterfactual that is impossible to answer with certainty, but that is worth considering. The engineering challenges that we have described, the development of the piston and cylinder mechanism, the development of the boiler, the development of the condenser, the development of the sealing technology, were substantial but not insurmountable. Each of these challenges was eventually overcome by the engineers of the 17th and 18th centuries, working with materials and with manufacturing techniques that were, in some respects, not vastly superior to those available to the ancient engineers. The question is whether a directed development program, funded by an ancient patron and conducted by the engineers of the Alexandrian school, could have overcome these challenges and produced a practical steam engine many centuries before the Industrial Revolution? The answer, according to most historians of technology, is probably not, or at least not without a series of prior developments in metallurgy, in manufacturing, and in energy supply that would themselves have required decades or centuries to achieve. The development of the steam engine was not a single innovation, but a cluster of interdependent innovations. And the development of any one of them depended on the prior development of the others. The boiler required strong iron or steel. The strong iron required the blast furnace. The blast furnace required coal. The coal required deep mining. The deep mining required pumps. The pumps required the steam engine. The circularity of these dependencies, each requiring the others for its own development, created a chicken and egg problem that could not have been solved by a single directed development program, and that required the gradual, uncoordinated accumulation of capabilities over many centuries. Let that sink in. The ancient world possessed the principle of steam power. The principle was demonstrated by Heron in the Aeolipile. The engineering capabilities of the Alexandrian school were among the most advanced in the ancient world, and yet the development of the steam engine was not possible in the ancient world because the development required not only the principle and the engineering, but also a specific set of supporting conditions, economic, social, intellectual, and material, that were not present in the ancient world, and that could not have been created by any single development program. The Aeolipile is therefore not merely a failed technology. It is a lesson in the complexity of technological development, a lesson that is as relevant to the modern world as it is to the ancient one. The modern world is full of discoveries that have enormous potential, but that have not been developed into practical technologies. Discoveries in fusion energy, in quantum computing, in advanced materials, in biological engineering, that are waiting for the specific set of supporting conditions that will enable their development. The Aeolipile reminds us that the development of a technology requires more than a discovery. It requires a world that is ready to receive the discovery and to convert it into a technology, and the readiness of the world is determined by conditions that are often beyond the control of the discoverers themselves. The question of what would have happened if the ancient world had developed the steam engine is one of the most fascinating counterfactual questions in the history of technology. If the steam engine had been developed in the first century of the Common Era, the consequences would have been profound. The availability of a mechanical power source that could supplement and eventually replace human and animal labor would have transformed the economy of the ancient world, increasing productivity, reducing the demand for slave labor, and potentially setting in motion the economic and social changes that, in the actual course of history, did not occur until the Industrial Revolution. The environmental consequences would also have been significant, as the burning of fuel to produce steam would have generated pollution and would have accelerated the depletion of forest resources that was already a concern in the ancient world. The counterfactual speculation is fascinating, but it is also humbling because it reminds us that the course of human history is contingent on specific conditions that are not predetermined and that could have been different. The Industrial Revolution occurred in 18th century England because a specific set of conditions, economic, social, intellectual, and material, converged in that specific place at that specific time. The same set of conditions did not converge in 1st century Alexandria, and the steam engine was not developed for another 17 centuries. The difference between the two outcomes, the difference between the ancient world and the modern world, the difference between a civilization powered by human muscle and a civilization powered by steam, was not a difference in discovery. It was a difference in conditions. Let that sink in once more. The principle was known, the engineering was possible, the demand was present, but the conditions were not right. And because the conditions were not right, the spinning sphere remained a curiosity. The steam hissed away unproductively, and 17 centuries passed before the principle was applied to the work that it was capable of performing. The Aeolipile is proof that knowledge alone is not enough. Knowledge must be met by conditions, by incentives, by capabilities, by a world that is ready to use it. and when the world is not ready, even the most powerful knowledge can be set aside and forgotten. The cultural memory of the Aeolipile, which was preserved in the manuscripts of Heron's Pneumatica that were copied and recopied through the medieval period, and that were translated from Greek into Arabic and eventually into Latin, ensured that the principle of steam power was not entirely lost during the long interval between Heron's demonstration and the development of the modern steam engine. The Pneumatica was known to the medieval Islamic scholars who translated and studied the Greek scientific texts, and it was known to the European scholars of the Renaissance who rediscovered the Greek texts and who were inspired by them to conduct their own investigations of pneumatic and hydraulic phenomena. The degree to which the Pneumatica directly influenced the development of the modern steam engine is debated, but the preservation of the text ensured that the knowledge of the Aeolipile was available to the engineers of the early modern period, even if they did not directly draw on it in their own work. The modern relevance of the Aeolipile story is considerable, because the specific pattern that the story illustrates, the pattern of discovery without development, is one that continues to characterize the relationship between scientific research and practical technology in the modern world. The modern research establishment produces a vast quantity of discoveries each year, discoveries in physics, in chemistry, in biology, in materials science, and in a wide range of other fields, but only a small fraction of these discoveries are developed into practical technologies. The valley of death between laboratory discovery and commercial application, which is a well-known concept in the modern innovation literature, is the modern equivalent of the development gap that the Aeolipile illustrates, and the factors that determine whether a modern discovery crosses the valley of death or falls into it are strikingly similar to the factors that determine the fate of the Aeolipile. The concept of technological readiness levels, which is used by the modern research establishment to classify the maturity of a technology from initial discovery to commercial deployment, provides a useful framework for understanding the Aeolipile story. The Aeolipile, in modern terminology, would be classified at approximately technological readiness level 3, corresponding to analytical and experimental critical function and/or proof of concept. The development of the Aeolipile into a practical steam engine would have required the progression through the remaining technological readiness levels, from level 4 through level 9, each of which requires specific capabilities and specific resources that were not available in the ancient world. The concept of innovation ecosystems, the networks of institutions, companies, universities, and government agencies that collaborate to convert discoveries into technologies, is another modern concept that is relevant to the Aeolipile story. The ancient world lacked the innovation ecosystem that would have been needed to convert the Aeolipile into a practical steam engine. The Martian provided the institutional support for the initial discovery, but there was no network of engineering companies, no venture capital, no patent system, no marketplace for new technologies that would have provided the economic incentive and the organizational structure for the development of the technology. The question of whether the modern world's innovation ecosystems are sufficient to ensure the development of the technologies that the modern world needs is one that the Aeolipile story helps to illuminate. The modern world faces a number of technological challenges, including the development of clean energy sources, the mitigation of climate change, the treatment of emerging diseases, and the management of natural resources that require the conversion of scientific discoveries into practical technologies on a timescale that is far shorter than the 17th centuries that elapse between the Aeolipile and the steam engine. The Aeolipile story reminds us that the conversion of discovery into technology is not automatic, and that it requires specific conditions and specific institutions that must be deliberately created and maintained. The connection between the Aeolipile story and the modern concept of technological lock-in provides a useful framework for understanding why the ancient world did not develop alternative power technologies. Technological lock-in occurs when a society becomes committed to a specific technological path And when the accumulated investments in the existing technology, the infrastructure that supports it, the skills that are needed to operate it, and the institutional arrangements that are built around it, create barriers to the adoption of alternative technologies, even when the alternatives might be superior. The ancient world was locked into a power technology that was based on human and animal labor. The infrastructure of the ancient economy, including the agricultural systems, the manufacturing processes, the construction techniques, and the transportation networks, was built around the assumption that power would be provided by human and animal muscles. The skills of the workforce were adapted to this assumption. The social institutions of slavery and of serfdom were adapted to it, and the economic calculations of profitability and of investment were based on it. The introduction of a new power technology, such as the steam engine, would have disrupted these established arrangements, requiring the development of new infrastructure, new skills, new institutions, and new economic calculations that would have been costly and that would have faced resistance from the established interests that benefited from the existing arrangements. The concept of technological lock-in helps to explain why the ancient world did not develop the steam engine, even though the economic demand for mechanical power was substantial, and even though the engineering capability to develop the technology existed, at least in embryonic form. The lock-in to the existing power technology created a barrier to the development of the alternative technology that was more powerful than the economic incentive to develop it, and the barrier was reinforced by the social and institutional structures that were adapted to the existing technology. The modern world is also subject to technological lock-in, most notably in the energy sector, where the accumulated investments in the fossil fuel infrastructure, the skills and the institutions that support it, and the economic calculations that are based on it create barriers to the adoption of alternative energy technologies, even when the alternatives might be superior in terms of environmental sustainability and long-term cost. The Aeolipile story, which illustrates the consequences of technological lock-in in the ancient world, provides a cautionary example for the modern world, which faces similar challenges in making the transition from fossil fuels to renewable energy sources. The relationship between the Aeolipile and the modern concept of stranded technology, a technology that is technically feasible, but that cannot be developed because the necessary supporting conditions do not exist, is one that deserves elaboration. The Aeolipile is the archetypal stranded technology, a device that demonstrated a principle of enormous potential significance, but that could not be developed into a practical technology because the economic, social, intellectual, and material conditions that were needed for its development were not present in the ancient world. The modern world contains many examples of stranded technologies that have been demonstrated in the laboratory, but that cannot be deployed in the real world, because the supporting conditions do not exist. Fusion energy, which has been demonstrated in experimental reactors, but which has not been deployed commercially, because the engineering challenges of containing a fusion reaction and extracting useful energy from it have not been fully solved, is one of the most prominent examples. Quantum computing, which has been demonstrated in small-scale laboratory prototypes, but which has not been scaled up to the point where it can solve practical problems that are beyond the reach of conventional computers, is another. Advanced materials, including room-temperature superconductors and ultra-strong carbon nanotube composites, that have been produced in the laboratory, but that cannot be manufactured at the scale and the cost that would be needed for practical applications, are yet more examples. The pattern that connects these modern stranded technologies to the ancient Aeolipile is the same. A principle has been demonstrated. The potential is enormous, but the supporting conditions that are needed for the development of the technology are not yet in place. The Aeolipile story reminds us that the gap between demonstration and deployment can be enormous, measured not in years but in decades or centuries, and that the closure of the gap is not guaranteed by the mere existence of the demonstrated principle. The specific conditions that are needed to convert a stranded technology into a deployed technology vary from case to case, but they typically include a specific economic demand that justifies the investment, a specific set of materials and manufacturing capabilities that enable the production, a specific institutional framework that supports the development, and a specific intellectual culture that values the application of knowledge to practical problems. The absence of any one of these conditions can strand a technology, leaving it in a state of perpetual potential that is never realized. The Aeolipile was stranded by the absence of all four conditions simultaneously, and the technology remained stranded for 17 centuries until the conditions finally converged in early modern England. The question of what the modern world can do to prevent the stranding of the technologies that are needed to address the challenges of the 21st century, including climate change, resource depletion, and public health, is one that the Aeolipile story illuminates. The deliberate creation of the conditions that are needed for the development of specific technologies through government funding, through regulatory incentives, through institutional support, and through public education is a strategy that the modern world can pursue and that the ancient world could not. The modern world has the ability to shape the conditions that determine the fate of its technologies in a way that the ancient world did not, and the Aeolipile story provides a powerful motivation for the exercise of this ability. The philosophical implications of the Aeolipile story for the concept of technological determinism. The idea that the course of human history is determined by the development of technology deserve consideration. The technological determinist view holds that the development of specific technologies is the primary driver of historical change, and that the specific characteristics of a society, its economic structure, its social organization, its political system, and its cultural values are shaped by the technologies that the society possesses. The Aeolipile story challenges this view by demonstrating that the development of a specific technology is itself determined by the characteristics of the society in which it is developed, and that the relationship between technology and society is circular rather than one-directional. The Aeolipile was not developed into a practical steam engine because the characteristics of the ancient world, its economic structure, its social organization, its intellectual culture, and its material capabilities did not support the development. The steam engine was developed in the early modern period because the characteristics of early modern England, its economic demand for mechanical power, its social support for practical innovation, its intellectual culture of useful knowledge, and its material capabilities in metallurgy and manufacturing did support the development. The technology did not determine the society. The society determined the technology. And the question of which technologies are developed and which are not is a question about societies, not about technologies. The recognition that society determines technology rather than the other way around has important implications for the modern approach to technological development. If the development of technology is determined by the characteristics of the society in which it is developed, then the deliberate shaping of those characteristics through public policy, through institutional design, through education, and through the allocation of resources is a strategy for influencing the development of technology. The modern world, which faces urgent technological challenges, including climate change, energy security, and public health, has the ability to shape the social, economic, and institutional conditions that will determine whether the technologies that are needed to address these challenges are developed or stranded. The Aeolipile story reminds us that the ability to shape these conditions is a responsibility, not just an option, because the consequences of failing to develop the needed technologies can be measured in centuries of delay and in the suffering that the delay produces. The relationship between the Aeolipile and the modern concept of path dependence in technological development deserves further exploration. Path dependence refers to the phenomenon in which the specific sequence of events that leads to a particular outcome determines the character of the outcome, and in which small differences in the initial conditions can produce large differences in the final result. The development of the steam engine followed a specific path, from the Aeolipile to the atmospheric engine, to the separate condenser, to the high-pressure engine, to the steam turbine, and each step in this path was determined by the specific conditions that prevailed at the time the step was taken. A different set of initial conditions, a different economic structure, a different intellectual culture, a different set of available materials might have produced a different path and a different outcome, and the history of human civilization might have been radically different as a result. The path dependence of technological development means that the specific technologies that are developed by a society are not the only possible technologies that could have been developed, and that the specific technologies that are not developed are not necessarily impossible or impractical. The Aeolipile, which was not developed into a steam engine in the ancient world, was eventually developed into a steam turbine in the 19th century, demonstrating that the principle of the reaction engine was not inherently impractical, but that it required specific conditions for its development that were not available in the ancient world. The lesson is that the technologies that a society fails to develop may be technologies that are waiting for the right conditions, and that the deliberate creation of those conditions is a strategy for expanding the range of technologies that are available to the society. The concept of lost futures, the historical possibilities that were not realized because the conditions for their realization were not present, is one that the Aeolipile story powerfully evokes. The ancient world possessed a possible future in which the steam engine was developed, in which the Industrial Revolution occurred 2,000 years earlier than it actually did, and in which the course of human civilization was radically different from the course that it actually followed. This possible future was not realized, not because the principle of steam power was unknown, but because the conditions for the development of the principle into a technology were not present. The possible future was lost, not through catastrophe or through deliberate choice, but through the absence of the specific conditions that would have been needed to realize it. The concept of lost futures is a powerful tool for thinking about the contingency of historical outcomes and about the role of specific conditions in determining the direction of historical change. The steam engine future was one of many possible futures that the ancient world possessed, and the specific future that was realized, the future without the steam engine, was the result of the specific conditions that prevailed in the ancient world. A different set of conditions might have produced a different future, a future with the steam engine, and the question of how different that future would have been is one that historians and counterfactual analysts have explored in detail. The environmental implications of the lost steam engine future are particularly thought-provoking. If the steam engine had been developed in the first century of the Common Era, the burning of fossil fuels would have begun approximately 17 centuries earlier than it actually did, and the accumulation of carbon dioxide in the atmosphere would have begun correspondingly earlier. The environmental consequences of an early industrial revolution would have depended on the specific fuels that were used, on the scale of the industrial activity, and on the rate at which the technology was adopted, but it is plausible that an early industrial revolution would have produced significant environmental consequences that would have manifested centuries before the environmental consequences of the actual industrial revolution became apparent. The lost futures of the ancient world serve as a reminder that the future of the modern world is also contingent, that the specific technologies and the specific conditions that will shape the next century are not predetermined, but are the result of specific choices, specific investments, and specific conditions that are currently being created and maintained. The modern world has the ability to shape its future in a way that the ancient world could not, through the deliberate investment in specific technologies, the deliberate creation of specific institutions, and the deliberate cultivation of specific values and priorities. The Aeolipile story reminds us that the future is not something that happens to us, but something that we create, and that the specific conditions that we create will determine whether the technologies that we need are developed or stranded. What does the story of the Aeolipile mean for our understanding of the nature of technological progress, the relationship between discovery and development, and the role of social and economic conditions in determining the fate of technological innovations? The first implication is a recognition that technological progress is not inevitable. The standard narrative of technological progress, which presents the history of technology as a continuous, upward trajectory from primitive to advanced, implies that the development of specific technologies is inevitable, that they will eventually be developed regardless of the specific conditions that prevail at any given time. The Aeolipile story demonstrates that this implication is false. The development of the steam engine was not inevitable. It was contingent on a specific set of conditions that were present in early modern England, but that were not present in ancient Alexandria, and the absence of those conditions delayed the development by 17 centuries. The development occurred not because it was inevitable, but because the specific conditions that enabled it happened to converge at a specific time and in a specific place. The second implication is a recognition that discovery and development are fundamentally different processes that are driven by different conditions and that require different resources. The discovery of a principle requires intellectual curiosity, observational skill, and the willingness to explore unknown phenomena. The development of a technology requires, in addition to the discovery, economic incentive, social support, material capability, and a specific demand for the product that the technology will provide. The conditions that promote discovery are not the same as the conditions that promote development, and a society that is excellent at discovery may be poor at development, as the example of the Alexandrian school demonstrates. There is a pause worth taking here. Consider Heron himself, working in his workshop in Alexandria, building the devices that he described in the Pneumatica. Heron was one of the most creative and most productive engineers in the history of the ancient world. He understood the motive power of steam. He demonstrated it in the Aeolipile. He applied it in the automatic temple doors. He was, in many respects, the person who was best positioned in the entire ancient world to take the next step, to connect the steam to a useful load and to create a practical steam engine. And he did not take the step. He was not stupid. He was not lazy. He was not lacking in imagination or in skill. He simply lived in a world that did not provide the conditions that were needed for the development of the technology, and the absence of those conditions was more powerful than the presence of his genius. The third implication is a challenge to the great man theory of technological history. The idea that technological progress is driven by the genius of individual inventors who, through their personal brilliance and their personal determination, create the technologies that transform the world. The Aeolipile story demonstrates that the genius of the individual inventor is a necessary but not a sufficient condition for technological progress. Heron was a genius. He possessed the knowledge, the skill, and the creativity to envision and to build devices that were among the most sophisticated in the ancient world. But his genius was not enough to overcome the economic, social, intellectual, and material barriers that prevented the development of the steam engine. The development of technology requires not only genius but also conditions, and the conditions are created not by individuals but by the economic, social, and intellectual structures of the society in which the individual works. The fourth implication is a warning to the modern world about the fragility of the conditions that support technological development. The modern world, which has benefited enormously from the development of technologies that the ancient world could not develop, depends on a specific set of conditions, economic incentives, social support, intellectual culture, and material capability that are not permanent and that are not guaranteed to persist. The disruption of these conditions, whether by economic crisis, by social upheaval, by intellectual regression, or by the depletion of the material resources that technology depends upon, could result in the stagnation or the reversal of technological progress, just as the absence of these conditions resulted in the stagnation of technological progress in the ancient world. The fifth implication is a reflection on the moral and the social dimensions of technological development. The Aeolipile story is often told as a tragedy, a story of missed opportunity and of wasted potential, in which the ancient world's failure to develop the steam engine is presented as a failure that delayed human progress by 17 centuries. But the story can also be told differently, as a story about the conditions that determine who benefits from technological development and who is harmed by it. The development of the steam engine in the 18th century, while it was an enormous achievement that transformed the material conditions of human life, was also accompanied by enormous social costs, including the displacement of workers, the exploitation of child labour, the degradation of the urban environment, and the acceleration of the depletion of natural resources. The ancient world's failure to develop the steam engine spared it from these costs, and the question of whether the benefits of the steam engine outweigh its costs is one that is not as simple to answer as the standard narrative of progress implies. The environmental dimension of the Aeolipile story deserves particular attention. The development of the steam engine in the 18th century initiated the era of fossil fuel consumption that has been the primary driver of climate change, the most serious environmental challenge that the modern world faces. The burning of coal, and later of oil and of natural gas, to produce steam and to generate electricity has released enormous quantities of carbon dioxide into the atmosphere, altering the climate of the planet in ways that are already producing significant ecological and human consequences. The ancient world's failure to develop the steam engine, while it may have delayed the material progress of human civilization, also delayed the onset of the environmental crisis that the development of the steam engine has produced. The irony is profound. The technology that the modern world celebrates as one of the greatest achievements of human ingenuity is also one of the primary causes of the environmental crisis that threatens the future of human civilization. The ancient world, which is often criticized for its failure to develop this technology, is spared from both the benefits and the costs of its development. And the question of whether the development of the steam engine was, on balance, a good thing or a bad thing, whether the benefits to human welfare outweigh the costs to the natural environment, is a question that the Aeolipile story forces us to confront. The sixth implication of the Aeolipile story concerns the relationship between technology and social structure. The development of the steam engine in the 18th century transformed the social structure of the Western world, creating new social classes, new forms of work, new patterns of urbanization, and new relationships between individuals and the state. The Industrial Revolution, which was driven by the steam engine, produced both enormous benefits and enormous costs, including the displacement of agricultural workers, the creation of an urban proletariat, the exploitation of child labor, and the degradation of the environment. The social consequences of the steam engine were as profound and as far-reaching as its technological consequences, and the story of the Aeolipile reminds us that the development of a technology is not merely a technical achievement, but a social transformation that affects every aspect of human life. The ancient world, by not developing the steam engine, avoided these social transformations, both the benefits and the costs. The ancient world remained an agricultural society, powered by human and animal labor, with a social structure that was adapted to the specific conditions of pre-industrial life. The question of whether the ancient world was better off without the steam engine, or whether it would have been better off with it, is one that cannot be answered definitively, because the answer depends on the values and the priorities that are used to evaluate the outcome. If the criterion is material prosperity, the answer is clearly that the ancient world would have been better off with the steam engine, which would have increased productivity and reduced the burden of physical labor. If the criterion is environmental sustainability, the answer is less clear, because the steam engine initiated the era of fossil fuel consumption that has produced the environmental crisis that the modern world now faces. The seventh implication concerns the role of crisis in driving technological development. The development of the steam engine in the 17th and 18th centuries was driven, as we have noted, by a specific crisis, the flooding of the coal mines that were being deepened to meet the growing demand for coal. The crisis provided the specific economic incentive and the specific institutional support that were needed to convert the abstract principle of steam power into a practical pumping technology, and the resolution of the crisis through the development of the steam engine produced a technology that was subsequently applied to a wide range of other purposes. The ancient world may not have experienced a crisis of comparable specificity and urgency that would have driven the development of steam power. The demand for mechanical power in the ancient world, while it was substantial, was diffuse rather than concentrated, spread across many industries and many locations rather than being focused on a single urgent problem. The diffuse nature of the demand meant that no single industry or no single patron had a sufficient incentive to invest the resources that would have been needed to develop the steam engine, and the development effort was not undertaken because the cost was too high and the benefit was too uncertain for any single investor. The lesson of the Aeolipile for the modern world is that crisis can be a powerful driver of technological development, but that the absence of crisis can be a powerful barrier. The modern world faces a number of challenges, including climate change, resource depletion, and population growth, that may eventually produce crises of sufficient urgency to drive the development of new technologies. The Aeolipile reminds us that the development of these technologies is not inevitable, and that the specific conditions that enable technological development must be deliberately created and sustained if the technologies are to be available when they are needed. The eighth implication of the Aeolipile story concerns the concept of appropriate technology. The idea that the best technology for a given situation is not necessarily the most advanced or the most powerful technology, but the technology that is best suited to the specific conditions of the situation. The Aeolipile, which was an ingenious demonstration of the reaction engine principle, was not an appropriate technology for the ancient world because the conditions of the ancient world did not support its development into a practical power source. The watermill, which was a simpler and a less revolutionary technology, was an appropriate technology for the ancient world because it addressed a specific need, the grinding of grain, using a specific resource, the energy of flowing water, that was available in many locations, and that could be exploited with the materials and the manufacturing techniques that were available to the ancient engineers. The concept of appropriate technology, which was developed in the context of international development in the 20th century, provides a useful framework for evaluating the technologies of the past and for understanding why specific technologies were or were not developed in specific historical contexts. The steam engine was not an appropriate technology for the ancient world because the conditions that would have made it appropriate, the availability of cheap fuel, the absence of alternative labor sources, the institutional support for technological development were not present. The steam engine became an appropriate technology in the early modern period, when these conditions converged in England and when the specific economic demand for a new pumping technology provided the impetus for its development. The Aeolipile spun in a workshop in Alexandria 2,000 years ago. The steam hissed from the nozzles, the sphere rotated on its axis, and then the fire was banked, the steam subsided, the sphere slowed and stopped, and the device was set aside. Another curiosity in a catalogue of curiosities, a demonstration of a principle that would not be applied to practical work for 17 more centuries. The spinning sphere is a symbol of what might have been, a physical embodiment of a road not taken, a principle discovered but not developed, a capability demonstrated but not exploited. The Aeolipile contained within its spinning motion the potential energy of an industrial revolution, the power to transform human civilization from an agricultural society to an industrial one, from a world powered by muscle to a world powered by steam. And that potential was left unrealized, not because the principle was lost, but because the world in which the principle was discovered was not ready to develop it. The Aeolipile is not a story of failure, it is a story of timing. The principle of steam power, which Heron demonstrated in his workshop, was eventually applied to practical work by Savery, by Newcomen, and by Watt, working in an England that possessed the specific conditions, the economic demand, the social incentive, the intellectual culture, and the material capability that the development of the steam engine required. The development occurred when the conditions were right, and not before. The Aeolipile is proof that the rightness of the conditions matters more than the brilliance of the discovery, that the world must be ready for a technology before the technology can change the world. The manuscripts that preserved Heron's description of the Aeolipile passed through many hands over the centuries, copied by scribes in Byzantine monasteries, translated by scholars in Islamic libraries, studied by engineers in Renaissance workshops. The knowledge was preserved, even if it was not applied. The principle survived, even if the technology did not. And when the conditions were finally right, when the coal mines flooded, and the blast furnaces roared, and the boring mills turned, and the demand for power became irresistible, the principle was there, waiting to be applied, waiting to be developed, waiting to transform the world, as it could have transformed the world 17 centuries earlier, if only the world had been ready. The Aeolipile is a reminder that the history of technology is not a story of inevitable progress. It is a story of contingency, of conditions, of timing, of the complex interplay between discovery and the social, economic, and material conditions that determine whether a discovery becomes a technology. The spinning sphere in Heron's workshop contained the seed of an industrial revolution, but the soil of the ancient world could not nourish it. The seed waited, dormant but viable, for 17 centuries until it found the soil in which it could grow. The sphere is still now, the steam is cold, the workshop is dust, but the principle endures, encoded in the physics of the universe itself, independent of any civilization, any era, any discoverer. The principle was there before Heron found it. It was there during the 17th centuries when no one used it. And it is there still, in every turbine, every generator, every power plant, every locomotive that converts heat into motion, every machine that takes the energy of burning fuel and turns it into the spinning of a shaft. The Aeolipile was the first. The world was not ready for it, but the world is ready now, and the legacy of Heron's spinning sphere is the modern world itself. The principle of the Aeolipile lives on in the modern world, not in the specific form of the spinning sphere, but in the general principle of the reaction engine that the spinning sphere demonstrated. Every jet engine that propels an aircraft across the sky, every rocket motor that lifts a satellite into orbit, every steam turbine that generates electricity in a power plant uses the same principle that Heron demonstrated in his workshop in Alexandria, the conversion of the kinetic energy of an escaping fluid into the motion of a machine. The principle is universal, applicable to any fluid and to any scale, from the microscopic jets that propel bacteria through water to the enormous nozzles that propel spacecraft into the solar system. The legacy of the Aeolipile is therefore not a specific device, but a specific principle, a principle that was discovered by Heron and that has been applied by every generation of engineers since the Industrial Revolution. The principle survived the 17 centuries between Heron and Watt, preserved in the manuscripts of the Pneumatica, waiting for the conditions that would enable its application. And when those conditions arrived, the principle was applied with a force and a scope that Heron could not have imagined, powering a transformation of human civilization that has been, for better and for worse, the most profound and the most consequential in human history. The Aeolipile is a beginning, a first step on a journey that took 17 centuries to complete, and that is still continuing. The journey from the spinning sphere in Heron's workshop to the turbines that power the modern world is a journey across time, across cultures, across intellectual traditions, and across the vast gulf between a principle demonstrated and a principle applied. The journey was long, and it was not inevitable, and the conditions that enabled it were specific and contingent. But the principle that began the journey, the principle of the reaction engine, the principle of steam power, the principle that Heron discovered and demonstrated 2,000 years ago, is the same principle that powers the world today. The Aeolipile was the seed, the modern world is the harvest. And the story of how the seed waited 17 centuries for the right soil is one of the most important stories in the history of human civilization. The dust of Alexandria has covered the workshop where Heron built his devices. The library is gone, burned or decayed or dismantled, its manuscripts scattered across the medieval world in copies and translations that preserve only a fraction of the knowledge that was once collected there. The Maution is gone, its scholars dispersed, its research programs abandoned, its legacy preserved only in the texts that survived and in the tradition of inquiry that it inspired. But the Aeolipile's principle survived. It survived the fall of Alexandria, the decline of the Roman Empire, the upheavals of the medieval period, and the slow recovery of learning in the Renaissance. It survived because the principle was not dependent on any specific institution, any specific patron, or any specific cultural tradition. The principle was encoded in the physics of the universe itself, in the fundamental relationship between heat and motion, between pressure and work, between the energy of steam and the kinetic energy of a spinning sphere. The principle could not be lost because it was not a human invention, but a natural phenomenon, waiting to be discovered and rediscovered by anyone who boiled water and observed what happened. The Aeolipile teaches us, finally, that the relationship between humanity and its tools is not a simple one. The discovery of a tool does not guarantee its use. The demonstration of a principle does not guarantee its application. The potential of a technology does not guarantee its realization. Between the discovery and the use, between the demonstration and the application, between the potential and the realization, there lies a complex, contingent, and unpredictable process that is shaped by economic conditions, by social structures, by intellectual cultures, and by the specific material capabilities that are available at a given time and in a given place. The Aeolipile spun in Heron's workshop. The principle was demonstrated, the potential was revealed, and then the world turned away for 17 centuries until it was ready to turn back. The story of the Aeolipile is the story of a world that was not ready, a world that had the knowledge but not the conditions, the principle but not the practice, the seed but not the soil. The story is a reminder that readiness matters, that conditions matter, that the world must be prepared to receive a technology before the technology can transform the world. And the story is a warning that the technologies of the future, the technologies that will determine the fate of human civilization in the centuries to come, will be realized only if the conditions for their development are created and maintained. The Aeolipile sits at the beginning of a story that has not yet ended. The principle that Heron demonstrated in his workshop in Alexandria, the principle that heat can be converted into motion, that pressure can be converted into work, that the energy of burning fuel can be transformed into the spinning of a shaft, is a principle that continues to be developed and applied in the modern world in forms and at scales that Heron could not have imagined. The modern steam turbine, which is the direct descendant of the Aeolipile's reaction principle, generates approximately 80% of the world's electricity, powering the grids that illuminate the cities, the homes, and the industries of the modern world. The gas turbine, which applies the reaction principle to the combustion products of kerosene and natural gas, propels the aircraft that connect the continents and the nations of the world. The rocket motor, which applies the reaction principle to the combustion products of liquid and solid propellants, lifts the satellites, the space stations, and the interplanetary probes that extend humanity's reach beyond the Earth. Each of these technologies uses the same principle that Heron demonstrated in the Aeolipile, the conversion of the kinetic energy of an escaping fluid into the motion of a machine. The scale has changed, the materials have changed, the efficiency has changed, the applications have changed, but the principle is the same, as fundamental and as universal as it was when Heron first observed it in a spinning metal sphere in an Alexandrian workshop 2,000 years ago.